Is it working? Yeah. Okay, so hello everyone. Thanks for coming. I'm Ederson de Souza. I'm a software engineer at Intel for some time already, and in the last 2.5 years I've been working with Zephyr. And this morning we'll be talking about, I'll be talking about, or you'll be talking about, the future of Zephyr device module. This is the agenda. I'll talk about current interest, what is the device module, and some topics, assorted topics about the future of the device model. A disclaimer, I'm no oracle, no seer, so it's not like I'm seeing this from the future and I'll be presenting to you. It's actually being built, I'm helping, and I need your feedback, actually. So this is to start getting some ideas, some use cases, some constraints. I have some code that I kind of prototyped for some of those topics, and I will need your feedback to evolve that. What is the device model? Well, basically it's how Zephyr model devices. So the life cycle, how do we define their APIs, how they connect, how devices work on Zephyr, how do we manage them. And in this slide, you can see a collage of some assorted issues and pull requests related to the device model. A parenthesis here, I wanted to have like a nice collage with newspaper headlines, but I'm no artist, I'm no designer, so okay, let me ask some of this AI stuff to do it for me. And why it created something that reminded the collage, the text was like alien, it's gibberish, it cannot create something with real text, so we have to resort to the software developer trying to be an artist here, so sorry for the not so beautiful collage. And some of the topics in there are related to the life cycle of the device, how we initialize them. Maybe we don't want to initialize them at boot as Zephyr has always been done. Some people want to extend the API, so you can like have new API on top of something instead of like having to create a totally new API for some specific device, and more. Actually, there are some of those issues are actually wish lists, so there are many things. And I want feedback, so please talk. Of course, it will be at the end, so I'll try to go fast to give some few minutes or several minutes to get feedback. Although the talk is about the future, the first topic is actually about the past, because last week the deferred initialization was merged. What is that? So far, Zephyr had been initializing all devices on boot before the main function of your application starts to run. And in some cases, you don't want that. If for some reason, maybe you have some device that won't be there, or won't be needed for some specific use, and well, they would be initialized. There was an issue for that, probably is one of those on the collage, and there was a lengthy discussion, started like in 2021, I think, yeah. And it was a really fruitful one. There's people come up with some ideas, they decided on one, try to implement that. When they implemented, they saw that wasn't that good, then try to implement another one. And finally, it was merged last week, and it's a really, really simple one. You just notate on your device on the device tree that's going to be deferred, and Zephyr will skip it during boot. So it won't be even checking. It use some linker trickery to separate the initialization of the code that initializes that device in a separate section, so it's kind of no overhead there. And then, of course, you want to initialize it later, so there's a new API that you can use to initialize the device. But this is about the past, but there's a lesson learned here. During the implementation of this, there was a detour. Some ideas appeared, a new pull request was created. It seems nice that there was some really nice features there, but there were a disconnect with the issue. So people that were discussing the issue were not on this second pull request, and so we kind of lost some institutional information about the issue. After some time, we got back there, we could get in touch with the people, so the lesson here is If your pull request starts to deviate a bit from the issue it was supposed to be fixing, try to get the people from the issue on your pull request, because otherwise you may lose some information and something completely different than was agreed will be merged. Talking about the near future. Why I call this near future? Because I have a pull request as a work in progress that touches some of this area, and maybe we'll start the discussion for this now. This is about the initialization order. So not only we want to initialize the device, but there's an order that we want to respect. This order basically comes from the device tree, but not only. We also have a priority that we can set for the devices, for the drivers when they are initialized, so that you can ensure that like some function that initializes some registers runs before you try to initialize the GPIO or some other hardware that you want to initialize. And this other function is, you use the sysinit macro to define a function that will be called at some point during the initialization. This point is defined by a priority again. This priority is basically a number that the smaller number will run faster, will run before first. And then you kind of have to tweak those numbers with the priority of the GPIO, for instance, plus the sysinit to get things done in order. And this is bad because those numbers don't track the dependencies. They are just numbers that you can tweak to get what you want. But if you change something in the future, or a new device you will need maybe to change all the numbers before and after to get there. So not ideal. I have sent some pull requests to fix some of those issues. So we don't want that. How does that work now inside Zephyr? Is basically we have the init entries. That's a section inside the Elf file. It's divided by levels. So we have like the pre-kernel, pre-kernel 2, post-kernel. And inside of each of those levels, we sort, like with linker script trickery, the sections. So every sysinit or the device init, device tree init function have a name that takes like the level, the priority, and sub-priority, and then sort this. So we can have like, so that's how the order is defined, then Zephyr will be looping over those init entries and initialize them. The init entry is basically a pointer, to a device and a function that will be called. If it's just a sysinit, it's just a function. You can check the order using westbuild-t init levels. It's helpful to debug. And here there's something, I'm not sure if you can see, interesting. This is from a real build. So I was getting the data there and trying to create this diagram. And note that the pre-kernel 140 and pre-kernel 140. So both the ECIA and the SOC inits have the same priority. But the SOC needs to go after because like it's an underscore, the next one, it's lexicographical order. If it was 000, it would be the other way. Suspicious. So how can we tackle that? Proposal, and this is the very first one, so I'm hoping to iterate that, is let's use the names. Which names? For the functions, for the sysinit functions, we can basically use their names. For the devices that you want like to be initialized before or after, right now I'm using the compatible, because it's a name that's already there. Maybe it's not the best name. Maybe we should have like, instead of using the compatible, we could use like just GPIO. But then we would have to name the devices like, this is GPIO, this is UART, this is UART early because it's another UART that you want to use on a different moment. So this macro basically defines the function that we're going to call. The first argument is like a semicolon separated list of all things, devices, and functions that you want this to run before. And the second is the ones that you want to run after. So if you go back, I want this SOC init to run before GPIO and after the ECIA. This is defined on code, but we need a way to override it. And I'm not sure a good way to override it. We could have like a separate file, but usually we don't want separate more files on Zephyr, so I decided to use the kconfig, but maybe this is abusing the kconfig. But basically in this initial prototype, you can aptly name your config that then will be looked to override the definitions on code. And being a kconfig, you could also use the prjconf. Maybe some of you noticed that I use serves as the name for the serves. And I've been told that this is old, Zephyr is more mature now, we don't want those jokes with Z or Z. So there's more parentheses here. I want to ask a question. Who thinks that Zephyr now is like more mature, doesn't need to have things starting with Z? And who thinks that Z is too cool? Okay, thank you. So how it becomes, basically. All that information, now we have a two-step build. This is kind of mandatory. The first step build, we just build it as is right now, because we want to integrate with Qt functionalities. We don't want to change the world. I mean, Zephyr doesn't shy away from changing everything from time to time, but let's try to avoid that. So to be compatible with what we have right now, we would build it. So every sysinit and device tree entry will be then read from the elf file, so we can see what is the current order. This is added on a topological list with the constraints like this comes before the other one. We then read the elf file again to read the service entries, the kconfig. We place this in this list, and then we sort it. This is done by a script, Python 1. So after this, we have like a topologically sorted list of entries. And we use that list of entries to create a linker script snippet that will be used to generate the order. So now the SOC init is properly after the CIA. I'm not sure if that's the right order, but I'm assuming it was working, right? There's no bug reports about this. And before the GPIO. And if GPIO is not enabled, remember that list can be a semicolon separated list. So you can say that, oh, I want the SOC init to run before GPIO or before I2C or before anything. If there's, then all these constraints will be added to the list, so the list generator will respect that. And if GPIO is not there, it should be fine. But if no, in this my first prototype, if there is no dependence, then I will error because maybe something is wrong, maybe you missed something. The the linker script snippet looks like this. So there's no sorting anymore. It's like a full split thing that was created by the script. And then we build again. Then we have the second step of the build. We build again. And ideally, it should be idempotent with what we have right now. So we should, if we enable this right now, it should just work. I'm not sure it does, because some devices have more than one compatible. I'm not sure how to handle that yet. And right now, I'm taking the first one. Using. It builds for the things I tried, but maybe it will break something along the way. Also, one thing to mention here that I was experimenting is like you could use that to a specific instance of a device, so a GPIO tree, the third instance. The problem is how to get that information, which one is the tree. Because I first tried to use that number that you get from the DT for instance array, but that number is actually arbitrary. You should not be using that. There's documentation about not using that. So it's not good. I thought about trying to use the ordinal, but then the ordinal is like crazy. Here, the ordinal for the first GPIO is 13. Starts, how do you get that? And probably changes with the build too, so not. I thought maybe mapping 0 to the first instance, 1 to the second, but then again, it won't be really good because now is another number to confuse. Maybe I should be using the address. I don't know, that's a question. And this is the link for the PR, if you want to look at it. I created as a draft, so I was kind of hoping no one would look at that because it's a draft, but there are some comments already. So you see, the device model is kind of important, and people are interested in it. So please comment there, and here after, I think I'm fine on time, so we'll have some time to discuss this one. For the not so near future, I also was working, prototyping some stuff, some ideas here, and I wanted a way to notify the application that some devices failed the initialization. You can do that right now. The application can get there's an API call that you get the first device in an array, and then you can loop iterate over it and check the state and the init result. But that's kind of boring. I wanted to see if could we notify the application, like if the application, a simpler API for the application. So the application kind of subscribes to a topic and get this information from there. And we have like a ZBus that does exactly that. So I got curious and I tried. Okay, it seems to work. So I kind of got crazy with this. I kind of found a hammer. So maybe I'm trying to treat everything as a nail here. But then, for instance, for the device, the deferred device, the device that you initialize later, maybe you want to know when the device was initialized. So could we post on some channel this information? It seems to work, although for this, one idea is maybe the I2C was initialized later, but now you have the sensor that's on I2C. You want to initialize it too, but then it will send a message to the bus. Maybe you are not using subscribers but listeners, and then the bus will be locked. So I decided to try to have channels per device. So that can be heavy. So there are some drawbacks. ZBus itself should be light, but maybe having all those channels. But if you don't use them, I can imagine that most of those will be compiled away. ZBus is actually needs the kernel, so it needs I think use semaphore, so you cannot use that for early stuff, but you probably shouldn't be doing much on the early initialization, so I'm not sure if there's value on telling at the beginning of the application that, oh, something failed. Maybe you cannot even respond to that. And the Trojan horse there is because I didn't talk about device notifications on the beginning, so it's kind of I tried that. I kind of tried to show this in this presentation. But it's also useful for another thing that people are desiring on the Zephyr device model, that is unloading a device, deinitializing a device. There are several use cases. I think that a natural one is if you are a bootloader entry and you initialize some device to do your stuff, then you want to hand over to the next bootloader entry, and you want to deinitialize the device to give the device in a pristine state to the next entry. That's a reason. Some other reasons are kind of suspicious because I think that they overlap with power management, because maybe you're trying to do a poor power management thing. Oh, I'm not using that device, let's initialize it. I'm not sure. And I'm not sure if, even if you are not trying to do something sketchy, how does that interface with power management? That's a question that I have for you too. Is it independent, is interdependent? Maybe if you want the device to deinitialize, you need to call some power management thing to turn it off, and then you deinitialize it from Zephyr, from the application. What about dependencies? What if you take away I2C? What about the sensors that are on top of it? Maybe those dependencies are optional, so shouldn't be a problem. Imagine in the sensor again, the sensor also is using GPIO to trigger something. If the GPIO is not there, it's fine. We won't trigger anything, but it's still useful. And how we would do that? I mean, one way is going the power management thing. You have a device get, device put, so you have count things. But I think that right now we are getting the pointer to the device everywhere on Zephyr and trying to sanitize that to be you get things, you put things. Sounds like a really, really big work. I may be wrong here, maybe not going the right direction. And there will be a long tail of subtle errors. So I'm kind of worried of this. And using the hammer again, maybe we could notify that the device is going down. And then if you care, the sensor could subscribe to the I2C channel, got the notification, oh, the I2C is going down now. Oh, maybe I should do something about that. And it seems to work. But of course, I did just some small proof of concept here. I have also a pull request. This is more WIP. It's kind of crazy stuff, but it shows Some really small examples of this usage: the device notifications, the device deinitialization. It doesn't do anything, it's just to probe the concept. And again, if you can go there and provide some feedback, this is a draft. I don't think this one had anything, actually. No one cares about device notifications, what is that? But I'm not sure, I didn't look today. So I think that's it from what I wanted to tell to you. And if I'm not mistaken, we have 20 minutes to discuss. So let's talk.
Yes, we do have 20 minutes. So first of all, thank you for your presentation. And the first question or comment?
What is the use case for overriding the priorities that you showed earlier with kconfig and so on? Why do we have to override stuff? We don't do that right now. Yeah.
I'm imagining like an application that added something new and doesn't care about some other thing that's there. I mean, I don't think about the use case. I think more about the possibilities. One thing that some pull requests that I have sent regarding the changing, the tweaking the priorities is usually something else changed. And then for that application, you need to change the priority of something. So I've seen applications that change the priority, like in the kconfig. So I don't want to restrict that possibility. I still want the applications to change something.
Hi, thank you for your presentation on this. Really good. So one thing, if we take what we have today, devices and sysinit. So one thing that's really missing from sysinit and from what I can tell from services as well, is the ability to, from the application side, determine if the service or the sysinit ran successfully. So have you considered a small API, like a services API for querying like devices ready, similar to services ready, that sort of stuff? And seeing that we just now have deferred initialization for devices, how about deferred initialization for services?
Well, starting from the end, I think it makes sense, to be honest. Maybe many of those things are actually moving things from the build time to the runtime to the side. I think this is a trend, and I think that's valid, actually. So, yeah, I think it makes sense. I don't know how, but it's a nice use case. For an API to say if a service did initialize correctly, that's good too. I mean, really, I think that's, I kind of think that right now the sysinit doesn't even have a return code, it returns void, so you wouldn't even know. So yeah, that's a good point. Thank you. Services, yeah.
On the services, what was the thought process on using a string versus kind of how we reference device nodes in other places? And then that opens up however, we have that whole infrastructure, whether it's by label or by, and so forth, so that you could, so I'm just curious as to why you started with a string there for the compatible.
Yeah, I started with a string because in my first iteration, I actually started with a separate file for that. So in the file referencing like the string is like more natural, and it allows to be overridden from like the kconfig or from another file. So that's basically the original idea.
Okay. And then the other one, just as I don't know, I know it's a prototype or it's early right now, but as far as the linker generation, are you doing that in some way to deal with other compilers that aren't GNU linker script?
The first prototype here, I just use something the normal stuff. So yeah, I'm actually curious about like some different tool chains. It may be a problem. I really want to test that.
So before I ask my questions, actually, what Kumar said about the linker scripts, we have an infrastructure in Zephyr that's not very widely used to generate linker scripts from CMake. So instead of hard coding your linker script in GNU-LD or LLD or LLVM LLD format, you can actually define your linker script in CMake, and then it gets generated. There's a backend that then can generate either LD or, for example, scatter files for the ARMS Clang fork. So that's one option going forward. My questions were, well, actually, they're not questions. They're remarks on the purpose of the init. You asked that you weren't sure that it was. Originally, I remember very well that the first use case that was brought up in the architecture working group and elsewhere was being able to have one single binary that you flash in different boards that have slight variation. So then, when you boot, you decide which revision of the board you're running on, and then deal with the difference in hardware. But I wonder if that particular use case is actually solved with the deferred init, because if you put all the devices that can change in your device tree as deferred, then at that point in the boot process where you know which PCB you're on, you can decide then. The reason some users want a single binary instead of compiling for different revisions of the PCB is that it's the way to test. So not to have one binary that can verify both in development PCBs and in production PCBs without recompiling. So that's for to make sure that nothing else has changed, so to speak. So that was one. But I wonder if that use case is no longer relevant for the init, because we have now deferred init. And then there was another use case that I think is valid still for the init. Is imagine you have a bus, right, I2C, for example, but then one of the lines, sometimes you want to use it as a GPIO. That happens depending on your limitations on pin. So you might want to shut down the peripheral temporarily, use the line as a GPIO, and then bring it up again. I've seen that in the wild for sure. Yeah, that's it.
I'm glad it's being recorded.
Yeah. While I'm walking over here, I've got a comment on, you made a comment about the power management and the integration of that, and I think coming in and out of power management states have the same challenges as what you're doing here at the very beginning of initialization order, because you also have the reverse of taking it down in reverse order potentially and stuff like that. So I think as we work through this, we have to keep that part in mind as far as what we're doing.
Regarding that, we also need, Regarding that, I think it's important to note here that, like with power management, at least the way we are doing that right now, I mean, when you go into a lower power state in a device, the device is still there. It's loaded and everything, and then you go in. So this is not the init per se, yeah, because depending who you talk to, this can mean that, hey, I am just going to unload that completely from the memory, in a destructive fashion, and then load it again. This is like, in Linux, removing a module and loading it again, something like that. Yeah. So I'm not sure about the use cases there, but now we have also the loadable extensions. This could be like something to look at. Yeah. My original question, I'm sorry for diversing, is regarding dependencies. What type of dependencies are going to be introducing, and basically in which direction? Because as you mentioned, we have device drivers, we have services. I mean, yesterday Rodrigo was talking about daemons and so on. So what type of dependencies would be possible with this approach, and where do we want to go? And just to emphasize here, what is really the main? I mean, how are we going? Is device tree going to be really the main thing that everything runs around it, or is device tree just going to be one service, let's call it like, or one subsystem that actually provides information into a bigger initialization type of service that we will have?
Yeah, the approach of like getting everything and putting on this topological list to sort it doesn't really matter from where the information is coming from. I started with the CZNIT, the services, but there is actually nothing preventing us from actually getting that from the device tree. The information doesn't need to be there somehow. And I don't see exactly why the limitations, but I mean, you can work around with like instead of before, after or something, but at some point that can be problematic. So I don't think that we should have any constraints there. If you want something to run, if you want to say GPIO runs after something, you should be able to. Right now it's not implemented, but I believe that.
I'll comment on the power management thing. It's like we have a chip that when it goes into the PM mode 3, it loses all settings. It's so annoying, and so so then you find you're just basically doing the whole initialization again, right? And so it's having a framework to just walk through it again would be pretty useful.
Yeah, so I see a lot of value in what you're talking about here, but one thing you didn't mention that we have today, I've been searching for it while I've been sitting here, but there is a kconfig setting to allow us to get a warning. I think it's a warning. I'm not sure if it's warning or error. Warning or error whenever you basically have priorities out of line. So for example, you have an I2C device that inits before the I2C bus. And at build time, you're notified of that. I honestly wish that were on by default, but that it's not. And once I found that, I was thrilled because it just is one less thing I have to check myself. What I would like to see is something along these lines, because it's imperfect. It does not take care of things like, GPIO has to be up before I2, something along those lines. So if we had these dependencies in place, defined in place, it'd be nice if we could extend that warning so it was a build time thing. So we could know at build time, you've got things out of order. And that way, low to no impact on code size. And just to comment on something someone else mentioned, they were talking about a service. If you could add an API to query is service ready? My only thought on that is I'd rather see it closer to how devices are today. If you're an I2C device, you check to see, is your bus ready? And I'd rather just see it follow that model. I think services should be same model. Services should be very much like devices, just maybe no hardware involved with the service. I do virtual device drivers already that are basically set in device tree, but there's no hardware associated with them, and I use that model. So that's...
Simplifying it with less things, it's always good.
Yeah, so this is actually riffing off of what Anas was just talking about. So the point being, obviously, that traditionally, we've looked at device tree as like a preprocessor that then compiles into a representation that happens to be this older sysnet thing. That doesn't need to go away, right? I mean, like, you can look at this the same way, and the only distinction is, that the thing we're compiling into is now mixed between these new service IDs, whether they be strings or compatibles or whatever, pick whatever that is, and these very strange looking pre-kernel 1, pre-kernel 2 early. I actually just literally had to go and look this stuff up. No one's ever really understood what those things mean, right? I mean, they kind of move around. Early is total voodoo. That happens before Arch kernel init, which is like different architectures do different stuff in there, and it's just a hook where you can do stuff in C. So whether something works in early, nobody really knows. Pre-kernel 1 kind of means before logging. Pre-kernel 2 means after logging, but before, right? So if you just take those moments, Arch kernel init, logging init, device init, right, and just turn those into IDs, the whole thing becomes just a single like array of compiled stuff. You don't need to worry about the older API. To the extent of compatibility, right? But we don't need to lose that, right? Like you can look at device tree as a preprocessor on top of this, and it just happens to be that the names in there happen to correspond to device tree if you've enabled it. But I don't know, that's what I got.
I'll say that the early just got added in a little while ago because it used to be the hook that the vendors had to fix any kind of weirdnesses they had with their chip, right? I only know this because I did a presentation several years ago about the whole initialization flow.
Don't use early, just go.
Yeah, don't rely on it.
It's there, you can do it, but you can also include it other.
While I'm walking back, I had one other question that I wrote down. You were talking about on a different topic about notifications. Have you thought about what your latency requirements are for when the notification needs to show up and stuff? Because I think that might dictate which mechanisms you want to use to make those notifications go around.
Yeah, that's a good question. I mean, I don't expect there will be too many notifications going around, and I'm kind of expecting that most of the notifications will actually be using the listener from the bus as kind of right on the EU run. So I don't think that will be like subscribing for things and waiting. I'm kind of expecting everything to be a listener.
So, having heard to some of the comments here and your presentation, and having been there when all of this transition happened back in the days in Linux, from CCV init to systemd and the whole fast boot and getting things to boot in 2 seconds and whatever, and people coming up with crazy ideas. But now, obviously, we have systemd on Linux. And when I see some of the concepts here, like with the names, and you're talking about external files and so on. Again, I'm not advocating for creating systemz or whatever. But there are a lot of things, lessons learned, and there's a lot of concepts which can be interesting, at least from this side of things, that we can look at and see how they make sense in our content. For example, I mean, we were talking earlier, you were talking about external files to define the dependencies. I mean, obviously in systemd we have the units where when it's very basic. We have also the init levels, the pre-kernel, 1, 2, kernel, post, etc. This could be also described as like, milestones in the boot process that different services and device drivers can depend on and so on. And you also talked about the labeling like device drivers with something a little bit more generic so other things can depend on it. So I mean, if you think about it, this is like coming close at least to the idea in terms of how, I mean, the implementation obviously will be different, but I would really encourage us here to start looking into this. I mean, we don't have to reinvent the wheel in terms of Linux is different, but I think there is a lot to learn from there, yeah.
Mm-hmm. Yeah, and one thing about systemd and those things is like they manage things in runtime. So it's not like this is kind of more a static approach, but maybe you want to initialize something later, like you have a crash and you want to start like some URs to send some information there. And that like could be nice if you could like, oh, I need the UART, and then all the dependencies are handled, and you can send the information.
So this question is coming from a place of ignorance, I suppose. But when I want to control the order that my peripherals initialize in and find out if they failed, I write code to do that. And then I come to Zephyr, and I see this auto magic with multi-build steps and no way to know if a particular device failed until there's an update to the ZBus API. And I, as a kind of a lower-end guy, go, what is going on here? Can you give me a little bit about why it's so complex to do something that seems simple to me?
If you had like a callback that on the early initialization, you can, oh, this failed. I mean, there's nothing much there. So we kind of, it was one topic discussed on the deferred initialization indeed. It could be potentially dangerous because what you can do on those early steps using the kernel is kind of limited. And if we kind of start using callbacks that are called on those early steps, you can like shoot yourself on the foot. So that's basically one of the things that we are kind of against having the callbacks at the early steps of the boot. And you can mess with the word there, basically.
Yeah, and just to answer kind of at like a higher level, it's just that we've got we're up to thousands of boards now, or over 1,000, I think it is. There's a lot of stuff in there, and if every board's got its own C function that's going to go through and initialize this and initialize this and initialize this, it becomes kind of unmaintainable. I actually was just in a talk about audio DAPM widgets in the Linux kernel, and they have a very similar problem where like every device out there in the world has this big topology that's listed in C code, and yeah, it just turns into a big mess. And so device tree solves that problem.
An application knows the order it needs things to come up in, not the order.
Well, yeah, exactly. They're more applicable.
Just to continue on that, briefly on that topic, on the complexity. So aside from what Andy just said, I mean, if you had for every single board and combination of kconfig option, imagine just have to have a board file .c with that sequence. I mean, for every board, right? It quickly becomes unmaintainable. That's for sure. But then there's also the fact that you want. Sorry. But this is maintainable. Yeah, I think so. If it's well written, why not? Yeah. Indeed, it is. It's a little bit like why device tree, right? Why device tree? I could have my header files enabling this, but have you tried then combining all support, sort of unified support for all types of boards without device tree? Then it becomes really unmanageable. So this is similar. It's about providing infrastructure that almost every embedded developer needs, but you need to provide it in a way that people can express it, if possible, in a data-oriented way. In this case, with device tree, and then it's verified by the system, and everybody uses the same system. That's the whole point of Zephyr. Otherwise, you do bare metal, but the complexity, in general, long term, is definitely worth it from my point of view because it gives you all of this.
Okay. Well, that alarm was the end of the time, so let's give him some applause. This is a really well engaging project. And he has a lot of links to PRs, so
Work to do.
so engage there and engage in the meetings, guys. Thank you.
Thank you.
This is why I always talk over time, because if you finish early, it goes to a big bike shed.
But that was the idea here, so I need to finish it early.
Most engaging talk I've seen so far, so yeah.
Oh, that's nice.
I have to say, I hate the fact that we split the sysinit from the device init stuff. Right? Because to me, I wanted it to stay kind of consistent model across all of them. And so that part annoyed me when we did that.
And you're good talk.
Thank you.
Concept actually comes close to something I've been working on with the services concept as well. I'm using.
Let me take it. I can stop.
Yeah.
I'd like to have a talk with you.
Hey, everybody. Thanks for sitting in my talk. I'm Mohammed Bilou, part of MabLab's Embedded Solutions, and we're going to talk about Zephyr and OpenAMP. And if you listen to my last two talks at FOSDEM and then last year's Zephyr Dev Summit, like a lot of these talks have been motivated by me being in close proximity to FPGA engineers. And so, this is the next iteration in that sort of kind of development process. I try to claim to be an FPGA engineer, but I still stick to the embedded software side. So just a quick agenda for today's talk. We're going to go over motivation behind what we're doing. We're going to talk a little bit about the OpenAMP overall framework and its relation to Zephyr. The system architecture for the project that I worked on, I had to change some things because it was a client-based project, but the overall kind of framework and structure was similar. So we're going to talk about what that looked like, the development process, and this is not a Yocto class, but just because of the nature of the project that I worked on, like there were some Yocto bits, so we're kind of go over that in a slide or so. Some common issues and like the resolutions that I discovered. So if you're also doing something with OpenAMP, that could be useful for you, and then kind of next steps to wrap it up. So just a little bit about myself. I'm an embedded software consultant. So I do a lot of design work that includes all sorts of verticals from medical devices to custom ASICs, which is the motivation behind a lot of the talks that I've been doing with FPGAs. If you know anything about ASIC development, the first thing you generally do is prototype it on an FPGA. So a lot of my clients recently are like, hey, this Zephyr thing is cool. We've been doing all of this stuff in FreeRTOS. Can we try to do things with Zephyr? So a lot of this has been some relatively new things that I've been working on, and it's been the motivation for these talks. You can follow and connect with me on my social media accounts that are listed down below. And then I have a newsletter that I distribute on a monthly basis, so if you want to sign up for it, you're welcome to, and you can find that on my website as well. So just a quick kind of summary about the motivation behind OpenAMP. So we have nowadays a lot of heterogeneous multiprocessor systems, and traditionally they have been on distinct silicon dice. So if you take the example of, let's say, a car, the automotive industry, you have different MCUs that are responsible for different kind of real-time subsystems. So you have an MCU that's responsible for brakes, you have an MCU, or they call it an ECU, responsible for like the shocks and suspensions, et cetera. And then so they all communicate using like some common buses. So in the automotive industry, that's the CAN bus. We can use UART, we can use SPI or I2C. So a lot of these different controllers, let's say microcontrollers, they communicate over these kind of distinct buses. And so in addition to an MCU that's responsible for some of the real-time components, you have an MPU that doesn't have any real-time requirements, but it's responsible, for example, in the automotive industry for the infotainment system. And again, they all have to kind of communicate over these pretty popular, these common buses. But recently, right, the silicon, as we all know, silicon density has exploded pretty substantially. So you don't have like a single CPU or a single controller on the silicon itself. You actually have a lot more hardware that's stacked on an SoC, right? So this is an example of an NRF52840 SoC, and we can see that they have a radio subsystem, right? Hardware to implement the radio subsystem, USB, all sorts of peripherals, and et cetera. And we can see that actually the core itself constitutes probably the least, one of the fewer in terms of silicon area. So nowadays we have a lot more going on in our SoCs beyond just the CPU itself. So what as kind of an extension to that is we can add, like a lot more silicon vendors now are adding microcontrollers and microprocessors onto a single die itself. So, we have an extension here where it's like, okay, you have different peripherals on the die itself, but now you're adding multiple cores and multiple controllers themselves also on the SoC. So the advantage of that is we can kind of distribute the workload of our application across the different microcontrollers and also even multiple MPUs as well. So for example, like if you have an MCU, that can be responsible for a lot of the real-time operations, going back to kind of like the automotive space. the actual components that are responsible to make sure that are safety critical. And then the MPU can be responsible for some of the non-real-time components. Another application for this is robotics, where you have, again, like the MCU responsible for actuation, and then the MPU can be responsible for like the GUI, display communication, things that are not real-time or safety critical components. So for example, now, if we look at an SoC that's relatively modern, and actually pretty modern and new, is we can see that we have multiple MCU cores or different types of cores and heterogeneous subsystems within a particular silicon itself. So you have multiple kind of Cortex-A cores, for example, on the NXP IMX8M+, in addition to like a hard DSP and a Cortex, an ARM Cortex-M device. And then on the newest kind of NXP SoC, the IMX95, we have actually multiple Core M devices along with a Core A device. So essentially, like, we can start getting creative on how we want to take our application and how to distribute it across our single silicon. And that kind of starts unifying a lot of how we can think about how to distribute this workload and also how to manage these different controllers. So, for example, if you were at Embedded World last week, you saw this robot from Tordex, and that had like basically an IMX8M+, SoC from NXP, and then you had basically the MCU responsible for the motor control and the actuation on the robot itself, and then the A-core, the Cortex-A ARM device that's on the same silicon was responsible for like the GUI, the interaction, and any sort of communication. So it's kind of an example of like, what sorts of capabilities you have on this, relative. It's a pretty small device, which is pretty cool, right? As you can see, like somebody's leg is right there. So, it's self-contained, it's pretty low power, et cetera, and physically small. Whoops. So what are the advantages of having this architecture where you have microcontrollers and MPUs kind of all in a single piece of silicon? We have increased speed and reduced latency, right? So that's huge, right? We don't have to have, relatively speaking, for example, like between, let's say the ARM processors, right? Like you can use like actually direct interconnects within the silicon itself instead of having like SPI, UART, et cetera. These are, relatively speaking, slower buses. So you have much increased speed and reduced latency. OTA becomes a lot more simplified, right? So again, all you need to do is you have some piece of memory that you're writing to, and then you can just dump your binary into that memory that's responsible for where the MCU is operating out of, essentially. And so so you don't need to get creative. You don't need to you can start standardizing the MCU firmware update process, because if you're kind of all, let's say, on ARM cores, right, you have kind of the general framework about shared memory between a Cortex-A, for example, and a Cortex-M, and then they're sharing kind of flash locations that are specific, then the Cortex-A can start marshaling the OTA process for the MCU for the Cortex-M itself, for example. So that kind of framework or that kind of mentality led to the genesis of like this OpenAmp framework, which you can find a lot of documentation on as a starting point on the GitHub repo. There's multiple components to it, and we'll get into in a little bit. We have, of course, the OpenAmp library. And so the two main components of it are the remote proc and the RP message. They're the core building blocks of this particular library. So these two components actually were originally committed to the Linux kernel by TI. So the motivation for these implementations were essentially allowing communication between Linux and TI RTOS, or what was then known as sysbio. So that was kind of the original motivation for TI starting this framework, and then it got picked up by OpenAmp, which turned into kind of this overall project and organization. And then they expanded what TI's work, what TI started, into a much more comprehensive and extensive library and framework. So this is kind of the overall motivation behind OpenAmp in general. So we have essentially a single kind of piece of memory that's essentially shared across, let's say, the different cores. We have the Linux and their application that's running on the Core A, the Cortex-A, for example, and then we have, let's say, the RTOS and the bare metal implementations on the different Cortex-M processes, right? So essentially, it's like this is all one big piece of silicon, And we're just kind of, we have to just be cognizant of how the different memories are distributed. So let's kind of dig into some of the actual applications and processes that are responsible or that kind of build up OpenAMP. So first we have remote proc. And what that's responsible for is to start marshaling, kind of writing or setting up the firmware on the MCU, for example. So one of the steps that it does is, one of the first things that it does is parses the ELF file. And so it's important for it to do that, so it's assured that it has the appropriate memory segments that are to be loaded. And this is going to be kind of important later on as how this ties into Zephyr. And so it loads the remote processor firmware, and then it also starts, essentially just kicks the MCU to kind of get it going. And then we have RP message, which is the actual communication mechanism between. So once you use remote proc to basically load the firmware and get it going on the Cortex-M, for example, RP message comes along, and you can use that to essentially communicate between, let's say, your Cortex-A MPU and your Cortex-M MCU. And that's a very well-defined format on how this message exchange occurs. So you have this standard framework to communicate between these different cores. Two more kind of implementations of these overall mechanisms is, one is virt.io, so it kind of abstracts out the inter-process communication. And again, it uses kind of the shared memory region between the processors. And then we have metal, which is essentially the abstraction of the underlying OS primitives that OpenAMP uses to ensure, that all of the communication between your different processors are efficient. They're not kind of just hogging, they're not just inefficiently implemented. So, kind of just looking at now that we have kind of an overview of OpenAMP in general, we have remote proc, we have RP message, and then we have metal. So just kind of a quick overview of where they reside within Zephyr itself. So OpenAMP itself is an external repo that's part of the modules directory in Zephyr. And then so we have the Zephyr implementation of OpenAMP, which is essentially this resource table, which we'll get into a little bit. And then there's an example that I use as my starting point in Zephyr, which is under sample subsys IPC OpenAMP resource table. So that was kind of the starting point that I used for kind of this particular effort. And these are the relevant kconfig options. So config IPM is kind of enables the OpenAMP, the interprocessor kind of communication subsystem within the IPC subsystem within Zephyr. Config OpenAMP basically compiles the OpenAMP subsystem, and then the resource table config options essentially enable kind of this resource table, again, because that's one of the things that remote proc uses, is it verifies that your ELF file has that resource table entry to make sure that there is actually shared communication, that the MCU is aware that what that shared resource is, so that it can communicate between the MPU and the MCU. So that's one of the first things that remote proc does, is when you actually and we'll see how that loading process works. It's very straightforward. One of the first things that there's like a kernel module on the Linux side that kind of checks and parses the ELF file to make sure that it meets certain requirements. If it doesn't, it kind of throws errors. But if it does, it essentially just starts the process of loading that into the MCU. And so one of the things that it does is it checks to make sure that this resource table entry is present in your ELF file. And then also, we need to make sure that because we're kind of the slave in this, as part of the MCU, we need to disable the option to make sure that we're not the master in the OpenAMP configuration, because it defaults to a yes in Zephyr kconfig. And this is basically an example, in that same example that I referenced earlier. This is just the overlay for the board file that they're using, which is a STM32 part. And this is going to be useful later on. So again, we can see that we defined two things. We defined the IPC shared memory, right? We referenced that to a region of memory that's defined by the vendor that is shared between the MCU and the MPU. And then the IPC itself is a construct that we can kind of create and use that for the communication itself. And then we can use which is typical in a lot of these multiprocessor systems, is we have this kind of mailbox configuration. So this was kind of the basis for what I did as part of this development effort. So kind of talking about the actual specifics of this project, and again, like I did it on a different piece of hardware because the hardware that was originally intended for the project was custom and proprietary. So I wanted to kind of see what I needed to do essentially to use like a commonly available like development board, and then see how that kind of takes me, how that progresses. So this was essentially, it's the same sort of Xilinx product, but just on a different board by a different vendor. It's a Digilent Genesis ZU. It has a Zinc MP sock, so that's essentially a quad-core Cortex A, and then a dual-core Cortex R. So it's not the Cortex M that we saw earlier in the earlier silicons. This is a Cortex R, which is meant for kind of real-time operations. So this is just a block diagram of the specific controllers within the MP sock. So essentially, we have the Linux side that's going to be running on our Cortex A, and then we have our Zephyr is going to be actually running on the 0th kind of Cortex R MCU. And then we need to define, again, like they call it an IPI within Xilinx land, like that's essentially going to be our IPC communication. And then the shared memory is what we define as a shared memory for the IPC as well, right? So we're going to need to define those in our device tree. This is, again, just kind of a block diagram showing from Xilinx's website like how this sort of implementation works. So on the Linux side, we have essentially the same sort of OpenAMP infrastructure, RProc and RP message, and then underneath that is the virt.io kind of implementation to serve as the implementation of these two constructs. And then similarly on the Zephyr side, we're going to have kind of the same sort of thing. We have RP message, and then because remote proc is only on the Linux side, we don't have that on the Zephyr side. And then the virt.io is simply going to implement the RP message on the Zephyr side. So the goal is essentially we're going to create a Zephyr binary that's going to be resident, that's targeted for the R5, and it's going to be resident on the A53 RFS. We're going to load the firmware from the Pedal Linux side, and then we're going to start it, and then essentially we're going to send a message from Linux to Zephyr, and the idea is that we should, the expectation is that we should get that message back on the Linux side as well. Okay. So how did I get started with this? So there's not a Digilent board in Zephyr at the moment, so I tried to find something that was close enough, and I found the Korea KV260 R5 board that is kind of present in Zephyr, and I use that as a starting point. And the first thing that I did was I wanted to make sure that my pinouts were correct, my clock configurations were correct, right? And I just got Blinky working, essentially. That's generally, when I want to use a new board or new kind of processor that's based on a newer board, that's usually kind of the first step that I do is just get Blinky working. And it's not kind of sufficient to just like, yeah, like just eyeball it and see that it's blinking like at 1 second. Like you actually have to kind of generally like hook up like a scope and see, okay, maybe 110 milliseconds, 100 milliseconds, et cetera. That gives you confidence that, okay, your clock configurations are correct. The next step is just to get like UART working. So if you have Hello World, that's higher confidence that your clock configurations are working because UART is a little bit more sensitive to kind of clock configurations, et cetera. So if your clock is off, you might be getting just garbled, data that's coming out of your UART. And so, part of this exercise also was, and we'll see later on, is like getting the Xilinx kind of tools like Vitus working with kind of Zephyr. So, typical flow is we have kind of debugger configurations that are part of Zephyr, and you can use command line or you can use like Nordic Connect, and then you have like a debugger built in. This is a little bit different because there's no native kind of Vitus support in Zephyr, so kind of had to like get some like janky setup going, and we'll kind of get to that, like what that looked like a little bit, and then what the next steps are for that. And of course, the last step is to test, right? So once we have that working, we needed to or before this is once you have Blinky working, then we needed to make the appropriate configuration and modifications to get that working with OpenAMP, along with kind of the Echo example that's in kind of the Zephyr samples. So on the pedal Linux side, I mean, it was pretty straightforward. We go through the pedal Linux configuration. It's not the kind of focus of this talk. So all we need to do is enable the remote proc kernel modules and drivers so that we have that capability in Linux, essentially. And then this is something that I needed to do, is to create the recipe in pedal Linux to add the Zephyr binary. So the process was, I'd build the binary. I mean, it was pretty manual. Like, you build the binary, the Zephyr binary, and then you kind of plop it down into your RFS or your pedal Linux build, and then create your RFS, and then load that on the Xilinx side, and then kind of get going from there. So maybe there's opportunity here to kind of make this more integrated, so that you have like a automated process where you can just build the Zephyr binary, and then kicks off like a pedal Linux build to kind of embed that essentially, and then you don't have to like do more manual steps. And like I said, like, this was an important step to help me kind of debug issues that I was running into, is to use Vitis as a debugger. And so it was pretty manual. Like, I had to copy over a lot of the source files. There's like a bunch of different configuration steps in Vitis itself to kind of let it know like where the source files were, like where they were, how to set up the debugger itself, and then kind of reconcile the symbols within the binary within the source files. But, like, it was painful, but at the end of the day, I got like a pretty nice debugger where I could debug Zephyr code on a Xilinx kind of FPGA through their native kind of debugger, which is pretty nice. So kind of, let's say, so once things kind of started working well through the debugger, like how do we actually kind of load the binary and get it going, right? So it's pretty simple, right? You just, because the binary is resident on like a known path in our RFS, you just tell it like the file name without the extension. You just echo that to the sysfs entry, and then you just echo start, and it kind of kicks the tires. And then once, and it was pretty fascinating because I had the Vitis debugger set up, I could just set a breakpoint, and then like once I hit start, you could actually see like the breakpoint in main kind of kicking, like, okay, this is actually kind of working. So it's pretty nice. So kind of pivoting into some of the common issues that I encountered, and could kind of share some of the lessons learned with you. One of the first things that usually that did happen is just issues in loading and starting the firmware. So the kernel module itself, like, again, if you don't have the appropriate entries in your ELF file, it's going to throw an error. And one of the biggest reasons was you need to actually define this config option, like config openamp resource table, is because it compiles essentially like resource table.c has an explicit entry for the resource table within your linker, essentially. So then within your linker script, and then it adds that to your final binary. So that's kind of the one common issue that that I think a lot of people kind of run into. That's important to kind of make sure that's part of your board configuration. The other thing was, and I see this kind of common as well, is like, okay, you got the like your binary is running, right? You can use different mechanisms to confirm that your Zephyr binary is running, but now when you start to communicate from the Linux to the Zephyr side, you get a seg fault, right? So like, why does that happen? So a couple of things to make sure that you're doing before, to make sure that you're actually doing to ensure kind of this doesn't happen. One is your IPC connected to the mailbox in your DTS, right? So sometimes that's not necessarily like a seg fault. It's just like nothing happens, right? Like I have a breakpoint where I have a callback set for when I get the message, but it never triggers, right? Well, do you have your mailbox set up to Zephyr IPC to make sure that communication is being received on the Zephyr side? You have to make sure that your SRAM, because in the normal kind of KV260 DTS file, the SRAM is not, it assumes like there is no other coprocessor. It just assumes that microcontroller is just by itself. And so you have to kind of update it to make sure that you're pointing it to the right memory location, to actually point it to the RAM is in the right kind of shared memory location that we saw kind of earlier. And then finally, did you make sure that your shared memory node is actually connected to your SRAM? So these are kind of the general 3 things that we need to make sure to ensure that we have kind of a successful communication between the multiple processors. So this is kind of like a detailed example of like what that looks like. So this RPU0 IPI is the interface, and then between like this, the IPC interface, which Xilinx calls IPI, and then here we can see like the mailbox that's essentially the entry between or the communication mechanism between the Cortex-A processor and the Cortex-M0. So this is the 0th MCU. And so all we need to do essentially is make sure that we enable that, and then in our overlay file, just ensure that we're setting the Zephyr IPC node entry to a reference to this particular mailbox. Okay. And then the other thing, like I said, is make sure that your SRAM location is correct. So the left is actually from Xilinx's kind of example on how they do OpenAMP with FreeRTOS. So essentially, we need to make sure that we specify these RAM locations in our Zephyr DTS and update that node appropriately. And then again, we have to make sure that our Zephyr IPC shared memory node points to the appropriate reference to like our SRAM node. And then the idea is that once you have these three components kind of all correctly configured, then you should have communication between the different co-processors that are resident on your silicon and on your system. So some of the next steps, of course, and I'm terrible at this, is to upstream, right? So add the board to like Zephyr, make sure it's there. It's a slight variation on the KV260, but again, I think having as much board support in Zephyr is pretty valuable. And then, like I said, I think it would be helpful for me to document the steps to get Vitis working with Zephyr, because I think that could be a pretty powerful tool for somebody else that's kind of using Zephyr with Xilinx products to be able to kind of step through using Vitis. So I think I have about 10 minutes for questions or comments.
Yes, we're at 12 minutes. First of all, thank you, Mohammed, for your presentation. Do we have any initial questions? I see one up in the front first.
Thank you for the talk. If I remember correctly, with STM32MP1, for instance, there were some concerns about OpenAMP and RP message throughput from the A7 to the M4. I think someone benchmarked it around 100K per second because it wasn't zero copy. You're always, managing this ring of shared buffers in SRAM. So if you want to do like zero copy transfers, is there some improvements that have happened in how that can be handled in OpenAMP, or is it better to just go below that and manage shared memory and signaling yourself?
Yeah, I'm not sure. Yeah, I haven't, this was kind of just a purely functional test. I didn't actually see okay, what the performance looked like. But yeah, I mean, it would be nice to see where that limitation, if it where that non-zero copy occurs across a different memory, and then see hey, is there an opportunity to just improve OpenAMP, and then maybe Zephyr could be leading the way to improve OpenAMP's performance essentially. So yeah, that's a good question.
So now you're booting the R core from the A core. You played around with the master function, so you first start Zephyr and then Zephyr starts your Linux kernel. So you have like a 1 second boot.
That's a good point, but how I guess so. You're assuming that the firmware is where would the Linux firmware and RFS be resident? You would have to kind of figure out a way to, it would be resident in Flash, right? And then you would have to instruct the Cortex-A to, or would you, I guess I don't follow what that.
I'm implementing OpenAMP with Zephyr on the 9.5, IMX
Okay.
9.5. So there we can use the boot fuses to launch Zephyr from the QSpy.
Right.
And then the idea is to implement remote proc the other way around. But as a stopgap right now, we're just going to boot first Linux and then the other way around. But the notion that you have this fast RTOS booting, doing your PIMUXing, and then 10 seconds, 20 seconds later, whatever, depends on your Linux, right? That comes up later then.
Right. I guess I'm just curious, how, are you triggering the Linux boot from Zephyr?
Well,
Or is that the idea?
That's the idea.
Like-
There's now is a different bare metal method for it, but
Uh-huh.
I was just curious because I now saw this master. It's like, oh, hey, cool. Maybe someone made that already.
No. One of the things that like I was thinking about is like, okay, like if we kind of go back to like the robot, right, that I showed earlier, like one of the things like, okay, while Linux is booting, you could still kind of use the display interface to have Zephyr kind of display like a simple message so that, okay, while Linux is still booting, you have something to kind of inform the user like, hey, like what's going on. But yeah, that'd be interesting to see like how does, because I mean, if you're on the same silicon, right, like you're getting power for both, right? So like how do you kind of stage it so that Linux boots after kind of Zephyr? So,
Yeah.
and what would be, just out of curiosity, like where do you see that being like valuable?
So we're looking also at robotics. So the idea is that Linux is quality managed from safety critical perspective. So that can die, that can reset, that can crash. So, and then the control loop is running on the Zephyr side. So especially that robot, it will trip over. If you're going to use Linux, if you have Zephyr, you have uptime, it shouldn't fall over. Just you have power and you can run your safety critical or control loops
Got
there.
it. Well, yeah, cool. That's
Yeah.
Just to mention here, you can also start Zephyr with remote proc from Linux from U-boot. So they can start together. But yeah, I don't have an idea right now on how to start it from Linux to start from Zephyr.
Right.
They can start together, like from U-boot of Linux. You can with remote proc, you can start the Zephyr core.
I guess it would be interesting to
see.
see like maybe you can have like an intermediary where you just have like U-boot like just sit there, and it's just waiting for like the remote proc from the Zephyr side to say like, okay, now boot, right? Because the firmware is already like it's there, right? It's resident on the flash. So okay, U-boot is just sitting there waiting for kind of, and then like once Linux boots, like okay, the Zephyr side can query, like send a message and get a message back to see if it successfully booted or not. Yeah.
Yeah, I've got a slight question or comment on OpenAMP, the protocol there. Are the messages fixed size? I mean, I think they are.
I think they're
And
well defined, yeah.
Yeah, and so one of the challenges that we've run into is like, it's like you want a version of it that allows you to have flexible sizes for things like a network coprocessor sitting off on the that you're using OpenAMP to discuss, and so we end up. I'm saying we, my company, we end up with a custom version that's kind of close, and I'm not exactly sure why we didn't try to engage with the OpenAMP community to see if we can't get that up there.
Mm-hmm.
And I'm not even remotely familiar with the underlying change they did there, but it was dynamic versus fixed was a problem for certain types of applications.
Yeah, I had the same issue when I was talk yesterday about VirtIO MMIO, that when you have that running underneath, you can run API message on that, but that's fixed size and small units. But then next to it, you can expose a VirtIO network interface, for example. And then you use shared memory and next to API message instead of on API message.
Any more questions, guys? Okay, well, thank you very much for your presentation.
Yeah, thank you.
Mic check, mic check. Okay, great. Okay.
Still 5 minutes left.
Yeah, I'll turn myself off maybe. Okay. Can you hear me? Okay, great. So let's start. Thank you all for coming. I know there's many cool other talks. There is like this LLXT just happening. Many people went there, so thank you for being here. And welcome to my war story project and demo. Well, maybe not demo, but a demo in pictures of developing an art frame in Zephyr. So let's start with a small caveat. The presentation title, like the bio of the presentation, includes Bluetooth, LiPo batteries, and hanging the frame, but it was too chunky. Bluetooth didn't fit with Wi-Fi, and I decided a LiPo battery is not such a big thing, no point, right? So sorry to all wall mounting aficionados here, like no mounting as well. So what is covered? Basically, it follows a fairly standard schedule, agenda. So like motivation, some steps. I will introduce a small prototyping framework I designed, a little bit about LED handling, HTTP networking, and more about 3D printing and designing. Some hurdles, some solutions to them, and future work, of course. So who am I and what I'm doing here? I'm currently working as 5G chip developer. I do firmware for a silicon vendor. I tinker with Rust, Zephyr, game engines, and basically embedded Linux. After hours, I co-lead a startup of mine called Sticky Pistons Studios, and I do some blogging as well. So if you'd like to see some of my hard work, then it's there. In my free time, doing sports, so going hiking tomorrow, I think. So yeah. Why do it? Mainly, I looked around my house and I just thought to myself, like, not enough art, not enough nice things. And then I thought, well, I can do some nice things. Like, I can design it, print it, program it, and I did it. And also, you know, most of you probably know that our job as, well, mostly embedded folks doesn't really, you can't really visibly see it unless you do, I don't know, some LED or a nuclear reactor or something. And then you see your work, yeah? Then you don't really, there is no place for mistakes. But with such a small, shiny project, you can easily prototype and see the effects of your hard work. There is also a cool project, like many cool projects, like the ZS keyboard, I think. I might have I remembered it wrong, or ZS watch, which really inspired me last year in Prague. Great project. If you didn't see it yet, then yeah. So how did I do it? Now is the time for the small framework of mine I devised. So basically, I divided it into steps. So step 0 is ideation. You find some inspirations on the web, go to conferences, talk to people. In my case, it was a fairly standard project like NeoPixels. And then you should choose the brain of the system. So either it is MCU, I don't know, maybe some PLC, maybe you need real-time requirements, so FPGA or ASIC, your choice. And once you've chosen it, you should validate it. So the earlier you validate, the sooner you'll get the answer, can I do this project, basically with, for example, Zephyr or some other system. And I will talk briefly about it in a moment. And start with a prototype. It's like even earlier than prototype. So in my case, it was a cardboard, as you can see on the picture. Then software minimum viable product, or prototype, I call it. So basically, you know what you can do. You design some fairly simple software functions or pieces, and you basically test them in isolation or together, your choice, on a breadboard or already using the prototype. Then hardware to put it all together, and that you can travel with it. I mean, I didn't travel with mine because it weighed a lot. And I think the border customs control wouldn't let me in with this. Anyway, software extensions, hardware assembly, basically, you can just add as many things as you want. But let me continue with the actual steps. So step 0, ideation. So as you can see, there are already a couple of shiny, cool projects similar to that. They have one thing in common, of course. They don't run Zephyr. Some of them are based on Raspberry Pi. The other one is using Teensy. And actually, the one in the middle is being sold for $200. So, you know, maybe you could make a buck out of this project, right? It's an open source, open hardware, except for the parts I didn't design. So feel free to take it. And yeah, so one thing in common, no Zephyr, right? So when did it all start? Like, and now is the time for choosing my board. And last year, I received a sample, this dev kit, ESP32C6, and I was very happy because it had RISC-V, and RISC-V is basically the cool thing right now. So I wanted to know more about it by, immersing myself in it. But then it turned out it didn't have any support. So there have been some major changes with the hardware model version 2 recently released. So right now it's a mess. You can contribute if you want. There are links. You can follow this presentation on the web. So yeah, that's a small call for contribution, for participation. So yeah, I settled with good old ESP32, so Extensa. As you know, LED connectivity and programming it and flashing worked out of the box, right? With Zephyr, it just works. With network, I had a little bit more of caveats. I will mention them just in a while. And there is, for astute watchers or readers, there is like the battery pack. Do you know where it might lead to? What kind of problem? Well, I will tell you in a moment. So, yes, step 1, validation. So it's basically assembling it, cardboard, having a LED strip, cutting it, assembling it, soldering it, and all should be fine, right? Well, it turns out that, like, on the right, you have what should be displayed. Maybe this slide is better. And on the left is what actually was displayed initially. So it turns out like I cut the strip and it was cut like in a snake manner. And I read the data like line by line, so I had to reverse it. Also, funny thing, I loaded RGBA images and tried to fit them into RGB buffer. So obviously it was total garbage. I fixed that and it suddenly started working fine. So then we validated it. We see that actually I can display something on it. Then probably, I thought to myself, like, okay, either Wi-Fi or Bluetooth, I will try to send something to it using some kind of application or web interface on my phone or on my desktop, be it. So yeah, this is basically how you handle, well, LED handling is just that simple. You just load you put the driver in, you put the device in the device tree, you get the alias from the device tree, you instantiate the device, and you check if it's ready, and then you load the data on it, and it works. Very simple. Networking is slightly more complex. It's basically like there is this small flowchart, I would say, of how it all works. So basically, we have a client that asks the server. They need to be connected to the same network, of course. Client asks the server, loads the website. Server serves the website to the client, and then there are a couple of endpoints. I'll show them in a moment that are that the client can call the host. And basically, once the image is loaded, so client does an API call to special endpoint, server does parsing of it, finds the magic number, which I added just for simplicity, to know when the payload starts, and it raises a semaphore, and the image is displayed on the strips. So it's very extensible. I added some other APIs. It's basically that simple. I based it on two demos. Basically, it's one demo, but one is single thread and other is multi-threaded. I had to modify some code because it was very, very basic, I would say. Like, there was no handling of endpoints, there was no handling of multi-packets and everything. I will think if I will upstream it, I think it might be worth. I don't know yet, depending on you guys. So here is how I add endpoints. It's also fairly simple. And then there's some code. I won't go basically much into the details, but it's basically just string comparing the method type and telling which endpoint we chose. Then we basically do string comparisons of the API routes, and if we don't match any, then we return an error. Here you can see that since it's called multiple times, I needed to know the way if the header has been already read. So I added a static variable, which is later being set in the bottom part of the picture. So I found the magic number. I can now continue with reading the payload and loading the image data. So yeah, that's pretty simple. Up here, you can see I'm giving the semaphore and the thread that's waiting on it. It's basically taking it and displaying the contents of the data to LED strip, basically. Some tips, because some things weren't really documented well. I didn't find some things. That's like that's a reminder to myself to put it in the documentation. Basically, I wasn't able to build the HTTP server example without adding this heap mempool region size. Otherwise, it would compare that I was overflowing sections. One weird thing, I don't know yet what's going on here, is basically I wanted to strip all IPv6 support, but it turned out if I stripped it all, then I got some random crashes on every second HTTP request I made to the server. And I still managed to crash the server sometimes when I do the request too soon. I didn't debug it yet, but yeah, as you can see, it's a work in progress. And of course, make sure IPv4 address that you assign in the project conf is free, otherwise you just won't get a server running. So yeah, that's basically what is being served when you run the demo. And you can leverage JavaScript or any other browser runnable scripting language or any language on the client side to be called whenever you want to upload something to the server. Well, let's face it, this board is not a monster in terms of power, right? So I couldn't do any hard image processing on it, so I'm doing it on my laptop or phone. So yeah. This is the JavaScript code. It's basically very simple as well. You just draw to canvas, resize the image to 16 by 16. One thing I could do, it's very blurry, as you'll see in some images. I should probably run some edge detection, like sharpening filters on top of it. That's great because this is very powerful. It can run everything, right? And here you can see my previous bane, like this pixel data length I +4 and new index that is +3, just so I could extract the data properly. HTML is also very simple. Yeah, and this is the result. Basically, I don't know why the Rust logo is here, but it somehow made it. And this is very basic UI. It can also be tweaked as much as you want, as long as your browser supports it, right? Yeah, so this is. So let's come back to the battery pack. So several days pass. I've been using the battery pack to power the breadboard with the strip and basically the ESP32. And suddenly it started to go dim, and blue and red, blue was not at all visible, blue LED color, green so-so. And then I thought like, well, maybe I ruined something on the way, right? So I thought some color calibration issue, right? But then I looked online, I was like, no way. Maybe timing issues on the driver. I thought like, yeah, the driver worked fine. I did nothing, I changed nothing. So as always, check your cables, check your battery pack. It turned out to drop from 5.2 volts to like 3-ish. So the red was actually powering on. It has like, yeah, that's right. It has 1.8. But the rest, yeah, they weren't working at all. So yeah. Let's now go through the hardware MVP. So basically, I didn't know any 3D design before. Like, I'm a software engineer by trade. So somebody once told me, don't learn FreeCAD. And I thought to myself, why? And they told me it's difficult and counterintuitive. So yeah, guess what I did? I learned FreeCAD. So this is basically the design of the backplate. It's, yeah, basically the truth is that vanilla FreeCAD is lacking many features. I'm wondering sometimes how some of them have not been fixed for such a long time. So for example, there is this notorious topological naming problem, which basically prevents you from renaming nodes on the tree or reassigning the nodes. Like if you have a body that you shaped, you could, move some stuff around. It's parametrical and everything. But when you touch something that shouldn't be touched, you get errors like this. So this is the report view window, and it tells you recompute failed. Please check report view. It is the report view window. So yeah, thankfully, on the main branch, something like that, having been solved for such a long while, that's weird. But there is a fork from Real Thunder, and it works around this problem basically very well. It allows for disjoint bodies. That's one of the things that the original repo is lacking. And it has really good errors, so I can really know which vertex is not touching the other vertex, or where is the problem. So yeah, I recommend it. This project was designed in DIY spirit in mind, so composable and IKEA-style hardware. So I printed everything. I then assembled it myself. No screws, no glue, almost. No glue, actually, in the final prototype. And this is the BOM parts list. It's all available on my GitHub. Most of the stuff you can, basically everything except 3D printed parts you can buy. And the rest you have to print or do, I don't know, out of wood or metal. So yeah, now let's go to 3D printing. I also didn't 3D print much before. I happen to have a Prusa. And 3D printing is usually not hard. I use PETG or PLA, and they should be fairly easy to use, unless the printer starts getting, not really, it's not doing well. So for example, I got spurious y-axis failures, I checked the belt tightness, I cleaned the bearings, and then I found out that Z offset was ruined. Here's the picture, there is a blob of something, there's a strip, a pattern, and then there is a blob, it's basically ruined Z offset. I also happened to clog the nozzle. So that's the part that extrudes stuff. And I had to do the cold pull. So yeah, that's actually how it should look like. That's the blob of something, and that's properly attached first layer. And that's, I don't know what happened here. That's the cold plug. So basically I heated up the Allen key, and then I put it into the extruder from above and had to cold pull the rest of the filament. Sometimes when you fail to do that, for many times you just have to just buy a new nozzle, and that's not really costly, but it's a pain to assemble and disassemble the other way around. So that's the first layer being printed. The printer goes brrr. So some takeaways from 3D printing, if I may. So you will fail a lot, so print small slices, as small as possible, preferably full size, because it turns out that the print itself takes space. So when the printer prints, it basically squishes a little bit to left and right. And this was the source, for example, when you're doing holes or something, you should take that into account and add or subtract 2 millimeters from each side, for example. So yeah, validate your assumptions. I happened to burn through entire 1 kilogram of filament. and half of it was basically to just make sure that everything clicks and sticks together. And bridges when the 3D printer has to go over a strip of air. So basically there's nothing below it and it just hangs a little bit, but it's fine at the end. So supports from PETG are terrible to remove. Don't bother. Like I read that, like I managed to injure myself because I put a support under a bridge, that was like 10 centimeters long. It was a pain. Anyway, the fun part, assembly. So basically, I just went through this to that to like the LED strip snake being there, my keyboard as well. And there is the breadboard still. And on the right, you can see like the clicked in strips. They're visible on the left. And basically, it was really satisfying because they all clicked together and it was like, you know, IKEA feeling. Then there is some test pattern being displayed. There is a PSU, which I'll tell you a little bit more in a moment. And there is the frame without edges. This is like basically, yeah, just assembly process. And about power. So I bought a very beefy PSU, 16 amps at 5 volts. And I measured then everything, and it turns out that at like full brightness of all LEDs, I only got 4.4 amps. But there is a graph here I blatantly copied from a website about this WS281B LEDs, and it told me that at full brightness it should consume 50 milliamps. Well, it didn't, but I ended up having a big PSU I can, you know, retrofit for something else. So software extensions, basically, yeah, as I said, I have some spurious networking crashes happening, I don't know why yet. I can add new endpoints and of course things I didn't add yet. So these are animations. I tried to add GIFs just before coming here. It turns out that, well, I would have to do it on the server side because JavaScript doesn't support it on client side in the browser API. I mean, I'll probably figure it out later. Automatic Wi-Fi connection and connection monitoring and restoring. Maybe add a small, well, one more LED to show the status of the connection on the box. Persistent memory storage, so like having some samples to show around, or they could cycle automatically, maybe adding a remote, UI improvements, of course. Streaming games over Wi-Fi, it's like 16 by 16, but then I do some retro computing. So I thought to myself, maybe I could write some small and funny games on that, and using smaller PSU. So some takeaways. So check for your board, well, check whether your board is supported as early as possible. Hack around and just try to prototype, just validate it as soon as possible. Contribute to Zephyr documentation. That's a note for me yet again. Of course, ask when in doubt. Like I had so much help in the Discord channel that I'm really grateful for, and people are, you know, replying almost instantaneously. That's really cool. Yeah, that's maybe obvious. Don't be afraid of new things, but we are all here, so you all like to learn. So don't listen to people on the internet. That's like one thing that's especially for me, especially with LED and people saying that FreeCAD is terrible. I don't know why. And yeah, 3D printing and designing are an iterative process, and you will fail a lot, and you will recalibrate your printer many times, and it will fail. Yeah. So as I said, some acknowledgements are due to folks from networking and Espressive channels on Discord, and folks from Espressive who are currently working on porting this ESP32 C6 board and some other volunteers. So that's pretty cool. Further reading, actually, yeah, this is the fork. This is a cool printer calibration. It like really, well, it wasn't 5 minutes calibration for me, but it was like an hour, but still it was fun. Much better than the ones that are shipped with the printer. NeoPixels resource, that's also pretty good. It goes into the driver details. And a cool blog about RISC-V and Zephyr I just added on top of that. Yeah, so I happen to have written 2 blogs on that already. I plan to do 2 more, maybe even more, I don't know. And I added some repo links. And as I said at the very beginning, this is open source and open hardware where I could do it. I still have to learn PCB design and all the cool stuff. But yeah, feel free to remake it and showcase it. And I think we have come to an end. Any questions?
Do you have any video of this in no?
I happen to have them on my phone. I can show you in a while.
Okay.
Because
I'm just curious after the whole talk to see it because it animates, right? It's not only static.
Well, so I can animate it by sending new images right now. I wanted to add like the GIF support, but I failed so far, and I just didn't want to do it. I will add it soon.
Great. And yeah, actually, one other question, if there's no others. How did you settle on ESP? Actually, not. I know you wanted to use the C6. It wasn't supported. Then you went to the 32. But out of, I know you wanted Wi-Fi, right? But,
yeah, I happened to have bought many years ago some like 10 of them in a pack. So then they were lying around. I was like, they're so cheap. I'll take one. If I burn it or do anything wrong, I have 9 more. So yeah, and there is actually a lot of support for drivers for the good old ESP32. So
right.
That's why.
Yeah, for sure. Yep.
I highly recommend you take a look at Fusion 360 by, what is it, Autodesk? It's free for non-commercial, and it's far better than FreeCAD.
Does it work on Linux?
Oh, okay.
See, that's like...
It works on Mac and Windows, so...
Yeah.
Okay.
Many people recommended me this. I actually did a little bit of modeling for my previous project in Fusion 360, but I did none in FreeCAD. So, but yeah, I'm using Linux, so that's the problem. Or maybe that's not the problem, right? That's like the advantage.
One more question from my side. It's you didn't mention the PCB I didn't see a PCB or how.
There is no PCB.
There's no PCB.
There's no PCB. It's all connected to pins of the ESP32.
Yeah.
There's a PSU. They share common power source.
Yeah, but then you have a development kit or it's a dev kit.
Yeah, right. it's like a ESP32 vroom, like the W
Okay,
room,
I
yeah.
see.
Yeah.
Right, got it.
So, yeah. Once I learn PCB design, then I will surely showcase this.
I was just curious. Okay, thank you. All right, any more questions? No? Then an applause for Jakob, please.
Thank you.
Thank you. Thank you.
Thank you.
Oh, hello, can you hear me? Is the sound fine? Perfect. Hi. It's really nice seeing all of you here. I really appreciate you coming here to listen to my talk. My name is Maciej Perkowski. I work at Nordic Semiconductor. I am a software test developer. You can find me at GitHub, and my handle there is Permac. You might also see me on Discord answering some of the questions on the testing or Twister channel mostly as Maciek. And today I would like to talk to you about PyTest test in Twister. The overview, we're going to start with simply answering why we even bother about talking about PyTest. Since we have Twister, what do they have in common? Why do we need it? Also a bit what is PyTest, how it is integrated with a Twister, and then I think what will be the most interesting will be the examples of how we are already using it, and maybe a bit shed of a light what we're going to do in the future, what we can do in the future with it. So obviously, why we even bother with it? And the bold statement is we want to improve the quality of Zephyr. This is like always nice with testing. You always hear test supposed to improve the quality of your software. But it's not all about the quantity, it's really about the quality. So we really want to test some new stuff that were not possible before with Twister. Because on its own, Twister supports quite restricted or limited workflow. Twister builds your application, it flashes to your device or starts the emulation for you, and then it only reads for the output from your serial or your fan in, fan out. So it doesn't allow to really interact with your test or do anything beyond this workflow. So, but of course, we would like to do something more. What if we want to be more Pythonic? What if we want to use some cool Python libraries that are there? Z-test and basically like tests in Twister that were existing, they were really focused on the C side of your application. But what if you want to be more Pythonic? What if you use those libraries there? Also, what if you want to communicate with our device during the test? It was not possible before. It seems quite obvious that, I don't know, if you're having like a shell application, you'd like to test, to give some input to it, and then read what will be the output. It was not possible before. Also, especially if you like to do some more setup, you want to do something on your host side. Maybe you'd like to start virtual server on your host that will be talking to your client app. Now it will be possible, and I hope I will show you in the further examples. Some extra tooling that you might use from the CLI, like MCU Manager to program your board to interact with the programming, or using CAN interface for communication. Or even further going on if we would like to use more than a single device talking with each other. So is it possible? So this is why we start thinking about adding PyTest to the picture, because it's quite popular framework. It's very often used in the Python community. And according to their documentation, it is a mature, fully featured Python testing tool that helps you to write better programs. Also, PyTest frameworks makes it easy to write small, readable tests and can scale to support complex functional testing for application libraries. So it's all quite bold statement. It's basically that's what we are all looking for. Is it true? I hope that after the presentation you will be convinced that, yeah, this can be true. So for the main features for PyTest, at least in my eyes, there are like two of them. Plugins is really cool feature because those are modules. They can implement hooks, and your plugins can hook into the module, into a certain place in your application, so in your framework. So like you can imagine you have like a place where you're collecting your test, and then you have a hook there. Your plugin can go in and do something, like maybe change the ordering of the execution, or maybe decide how to parallel the stuff, or maybe apply some filtration. Also, you can apply the hook on the other end. When the tests are done, you have your reports, but maybe you want to have the report in the other style. So hooks allows you to really easy inject some pieces of your or other modules to do some stuff with your data, with your tests, or the framework itself. And in fact, that what I'm going to be presenting is actually a plugin to the PyTest. So the integration with Twister on the PyTest side is done as a plugin. So you add a plugin to PyTest, and it allows to recognize what Twister wants from it. But in general, plugins, in our view, won't be that interesting because they are mostly focused on expanding your framework, whereas, as you'll see in a second, PyTest here is just an executor. Twister is a full framework. For us, the most interesting part will be fixtures. They initialize test function. They are really test-oriented. So They provide you building blocks that you can reuse in multiple tests. They have very explicit namings. They are really easy to pull into your test. You don't have to think where they are located. You just really use the name in your test that you're going to use this fixture, and PyTest will do everything for you. Also, they are very modular. One fixture can consist of many other. They can build full stacks of them on top of each other. And they scale really well, both in complexity and also in the scope. And also what is very interesting with them, they provide a safely managed setup and teardown for your test. On this slide, I wanted to present what is the general idea behind how the PyTest was integrated with the Twister itself. This block presents like the generic workflow of Twister, where it first collects the test based on the YAML files, and on the left you see an example of such YAML file. And then it generates the test configurations, apply filters, spawn workers, and then start the cycle where the application is built, executed, and verified. So when we are up to the execution, the main question is being asked, is it a PyTest test or not? If it is PyTest test, then Twister will prepare and call a very certain command for the PyTest as an executor. PyTest will do some stuff on its end, like flash the device, interact with it, collect the results, and then as the output, it will prepare the JUnit XML report, and Twister will read this exact report and parse the result out of it. So the communication as an input is a very specific command for PyTest, what to do, and then on the end, we are looking at the JUnit XML report. So the integration is at this kind of level. PyTest runs here, it's put like in a different color, because this runs as a sub-process. And the idea behind like the requirement was that it should supposed to be like very seamless experience for the user. On this slide, I'm just showing you the typical Twister command that you're gonna call, pointing to a location where our test is sitting, telling that we're gonna run it on native POSIX. And then basically it looks like any other test from the Twister user perspective. What is highlighted here is just that you see that there was a test passed in less than 2 seconds on native POSIX. And that's it. So it looks like any other Twister output. So you don't know that was even PyTest in the background. But however, this is the place where actually you start seeing where all the seams are. Because it's supposed to be really seamless for the Twister user, but it's not that obvious from if you're coming from the PyTest community or more like how it is developed. Here you can see all the seams. Because what we are doing, we are calling in a very specific way. If you want to replay the PyTest test, can you do it on itself without Twister? Yes, you can. Maybe it can be a bit more complicated, but not that much. First of all, the easiest way would be to call Twister with extra verbosity to give you this exact comment which is using to call PyTest. So for instance, you would like to just tweak with your test, run it multiple times. You don't want to wait 15 seconds for all the collection and all doing on, but maybe like just 2 seconds to get the test result. So you can call PyTest on its own by copy-pasting this command. And in this command, there are several interesting parts. The first, this command actually is like combination of 2 commands. And you don't see my mouse, but on a second line, will it work? Sorry. Oh, you see. Here, in fact, these are 2 commands. First one is exporting the location of the plugin to the Python path, so the PyTest can pick it up. And the idea behind this was the requirement was that it's supposed to be really seamless, and Twister is developed as a part of Zephyr. You would get it by checking out the tree. You install nothing. And this was also the requirement for the plugin. You don't want to install it. You don't want to handle which version to use. It should come as a part of a Twister itself, as a part of the Zephyr tree. You don't want to install it, which is also maybe a counterintuitive to what people dealing with PyTest are used to. But then PyTest is being called. We are telling that we're going to use Twister harness. Also, what is important there that we're going to tell where the build directory is, so where our application is located, so where it can pull it in. That we're going to need this JUnit XML report so that Twister can read afterwards, some logging parameters, and also in the end we need to pass what type of device, so which adapter will be used. Will it be native POSIX or will it be hardware? And of course, obviously, that we're going to need our plugin that we wrote for PyTest to understand what Twister wants from it. I mentioned that you need to pass what type of devices, and this leads us to the idea of device adapter we have in the plugin itself. It's nothing new because all of this, you also have it on the Twister side. They are called like handlers, but we do a bit of refactoring, a bit of more abstraction to get a bit better in our eyes organization to allow for easier expandability of adding new adapters instead of like copy pasting. So at the bottom level, there is device adapter, which is an abstract base class. So it just provides you the ideas for the methods it's going to use. And this is not a full class, it's just a snippet of the code. So you can have a write method, which is responsible to write data to your device. It's going to check if device is connected. If not connected, it's going to give you error. And then it's going to use this kind of internal method called write to device. And the write to device is an abstract method. Abstract method means that if you don't implement this particular one in any module or any class that will inherit from that one, you will get an error. So this is a method to make sure that your interfaces are aligned. Because in your test, you will just going to call dut.write, and you don't want to bother if it's like QEMU underline or is it hardware. Because below, you can see that they are the real adapters. So for hardware adapter, write to device will use a serial connection and write data there. For QEMU adapter, the fan in, fan out will be used. The next interesting part of the usage of PyTest are the fixtures. And fixtures are these core building blocks of your test that you can reuse in many other. And here's like an example of some of the fixtures that are already implemented for you in the solution. So first of all, you need to mark that a given function will be a fixture, and you will use a decorator, pytest.fixture. And you can also provide what will be the scope of the fixture. So how long should it live? Should it be only set up once for the whole session? So each test will use the same fixture, or maybe it should be each time for every test, setup and teardown should happen for each single test. It will make maybe more sense on when we are looking at the real test. And the fixture, it's also preparing you like the setup and teardown. So all these parts up to the yield part is a setup. As a setup, we will try to figure out what is this device type being used, and then pull the proper adapter using the factory, and yield this device object. So this is like a setup. Then yield returns the object to the test, and after test is done, the code is coming back here, and the finally part is going on where we make sure that device is closed after the test. And with this example, I wanted to show you that the fixtures can be also modular, because as you see, this DUT, device under test fixtures, it uses the device object, so it's using the one from the top. And also they can have quite a configurable properties. So if you look here, the scope, it's using determine scope variable, but in fact this variable is a function. And this allows to decide from a top level, like if you declare in your test YAML that you would like to use a given fixture for the whole session, so you don't want to reflash your device every time for every test, but maybe you know what you're doing, you just want to like reset the device between each test, not to waste time on flashing, you can define the other scope like the session. And this will be figured out based on this mechanism. And again, it will first pull off this device object, and the difference is that this fixture DUT will launch the object for you and return the object which is supposed to be already prepared for the test. And at the end, it will initialize the close procedure. So finally, we came up to the examples of the tests. So we can have a shell interaction test. And this is not the real test for the shell module. This is like an example how the shell module can be used in your test. Because here, this is like a full file of the test. And as you can see, there are only like 2 methods. We're only probing a minor part of the shell module. Also, what is interesting that to get a fixture, you just use it in a test definition. We are importing the shell class, but basically just to give the syntax for the typing and to help our IDE to pick up which are the properties of the shell. But you didn't even have to import the shell. You just use the name shell, and PyTest will figure out. It will have the list of fixtures that will define for you. and you will be able to use it. And the shell fixture is another layer is built on top of the device fixture, and it just adds some extra handling, giving you methods for read and write over UART, over the shell. And in principle, that you just going one step further, so your device is ready when we get the prompt. You have a prompt, and this is the moment when you can start your test and start interacting. And here, this is very straightforward. We use this shell fixture to execute command help. So this is like it will use a write to our device. We get the output as lines, and then we're going to assert that somewhere among the lines we have the available commands, and our test is passing. And the other one is basically doing the same. It's just using the other command. We are executing command kernel version and try to verify that among the output we have Zephyr version string printed. So to see it in action, this is just oops, sorry. Maybe it wasn't the best idea to use this kind of interactive outputs here. If I just turn it off and turn again. OK, doesn't matter. Well, what I wanted to show you on that slide was that in the output you will see quite a nice. So if you call with extra verbosity, you can actually see everything what is going on with your. Nope.
You can click on the shared screen.
OK, let's not waste time on it. Sorry for that. I guess when I switched to the pointer, everything crashed. So yeah, basically, here I wanted to show you that how this test looks when you look in the output. So if you look at the output, if you run it, you will see that there is like when PyTest is kicking in, it will first print you the lines that, OK, this is a setup session. We're going to wait for we're going to use the hardware device. We are waiting for we're going to use a certain device, certain port, where we will communicate. And when we get the prompt waiting for us, this is where the test can kick in. And then we will do testing. You will see that we send an input to the command, all the output that came out of the command, that output was successfully verified, and then we can do the teardown procedure. And also what I wanted to show you on this example, that here with this fixture, they don't define the scope. So by default, it is a test, it is a function scope. So every single test will have its own setup and its own teardown to keep the isolation of test principle. So we will see that flashing is happening before every test. Another example is that, so what more you can do? So the first one was quite simple, showing how you can interact with your shell. The other one is a bit more complex, showing you that you can start doing some more stuff, actually start doing stuff with your device. And this is an example for testing MCU boot, so the bootloader, and the test is using MCU Manager, so the CLI tool that provides you interaction with your device. And this is an example of test downgrade prevention. And this is only a couple of lines out of the test. It's not the full test. And again, I'm going to focus, it's going to use the device adapter. It will use the shell. And also it will use the MCU Manager. MCU Manager fixture is also defined in the top level for you. And it's just a wrapper over this MCU Manager CLI tool to simplify. You don't have to write every time exact command what you would like to do, but it's just wrapping over the most typical interactions that you would like to do. So in this test, we will use a shell to first check out what is the version of the application we built, and if it's matching the one from our configuration. Then we will call create sign image, which is using West sign in behind to sign your image with a certain version, and this version is lower than the original one. We have to disconnect from our device because MCU Manager will use the same serial line, so to be able to get the connection to it. MCU Manager will do the image upload and reset the device. And again, we'll have to connect to get the output. We are reading the output until we see that the launching primary slot application, so basically the whole procedure ended. And also, we want to verify it in our output there are no lines that will match starting swap using move algorithm, so we will make sure that the swapping mechanism didn't start it. We actually want to make sure that the line erased due to downgrade prevention happened. And at the end, just to be sure, we would like to verify that when we ask through the shell what was the version, that this is the one that was at the beginning, that the downgraded one wasn't applied. So it's already showing you that you can do a bit more, not only talk with your shell, but maybe also use external CLI tool to also do something with your device. And in the end, I think it's the most complex example, which is I think really interesting because it is a full end-to-end test. It is using the LWM2M, and it's the test for interoperability, and it is using the Leshan demo server. What is really nice that is based on Open Mobile Alliance specification. I really recommend you to go to that link and to see how it is implemented. There is really nice README file there, also pointing each certain test from the specification one by one, is it implemented or not, and all of them are implemented. Also, they provide you the ways and describe how to be able to reproduce the test, because it requires a bit of extra tooling, how to set up your virtual network. You will need also like this Leshan server and other tools, but luckily they provide a handy Docker image that you can, and a quick description how to use it so you don't have to install all of this stuff for you. And what I wanted to focus is this test is really full end-to-end. So we will have our virtual network that is controlled and started by PyTest with Twister. Also inside there is sitting this virtual Leshan server. There is also the device under test, so our client application. And it can be, in this test it will be QEMU or native POSIX, but in fact it can also be like real hardware. This is this scales or can be used on other devices. And server will talk with the client using multiple protocols, but also our test can be talking with a server, with REST API, both ways, and also communicating with the client both ways using the shell. And to just show you how the test looks, this is using the nomenclature from the specification, and the test is using the shell, so the one you already see. It's using the device adapter that you see, but it also introduces the Leshan fixture, and Leshan fixture will start this virtual server, do all the setting for you, and also it will use an endpoint fixture which will create the endpoint for you. And this is an example of the registration update test. And in it, we will use a shell. We're going to push a command LWM to read 101 to our client. So basically, we are asking about this address. In this address, the lifetime is supposed to sit according to the documentation. So we're going to read it as our output. And the first line in the output should be this lifetime. Then we're going to modify the lifetime, just adding some value to it. We're also going to read what is the current time. And we're going to use the server. We want to write to the server, to our endpoint, to the 101 location, the new lifetime value. So we are pushing the updated value to the server, but then we are again reading from a device until we get update done. So server will push the value to the client, and on the client side, we are verifying if the update happened or when it happened. And again, we're going to ask the server to reach to the client and on a certain endpoint to first get the output, and among the output, we want to see where actually was the last update. So we want to verify that the value of time actually matches the time when we send the update. So it's not somewhere from the past, it's not somewhere for the future, it's actually aligned with the moment we send the value. And also we want to verify if this lifetime is the lifetime we updated to. So actually if all the process happened as we wanted. So as you see, it's like we can interact with multiple agents, with the server, with the device. They both talk with each other. So it's really like full end-to-end test, finally possible. And maybe what is interesting to highlight here, that I hope this maybe it's clear that this kind of test is quite readable. And if you really take like the specification and all the steps which are in your specification, like a cookbook, here's all the like implementation of it, all the steps that the test is doing. So I think it can really, of course, there's a lot of stuff going on behind. You need all of those fixtures and they do the stuff for you. But I think that it can really allow to give a really simple framework to script all these kinds of interactions. So what is the future? Of course, we would like to start adding more tests. There are not that many tests using PyTest added. I think it's in the tree for maybe a year, but there are not many tests yet using this tool. There are also, I believe, many low-hanging fruits that are, in particular, that use shell for different stuff. And you can find many of them marked using harness keyboard in the YAML, because this was the way before to just tell Twister that actually we don't know how to execute the test because you will need some interaction. So right now you can just, in many cases, you can just copy-paste the shell example, which I showed you before, just replace the values you want to put in your input, the values you'd like to verify, and you might be ready to go. Also, we'd like to test more protocols. I have a quick chat with Briggs. He's apparently already working for using PyTest for testing the CAN bus. But of course, there's more and more. But not everything is possible yet. Like the topic which is not properly addressed is handling multiple images. And especially if, of course, we have sysbuild that allows to build multiple images, but we want to go a bit further. Like we want to reuse the images between different tests. For example, if you have your Bluetooth test, when you have your central and peripheral, you don't want to rebuild central every single time. You want to build it like once and maybe using different variation with many different peripherals in different tests. So this still will need to a bit more thinking how to add this layer to Twister. Twister doesn't support it yet. And further, having multiple devices. What I show you, all of them are using just a single device under test, but maybe at one point you would like to have multiple devices talking with each other. What I show, it's possible to talk with a host. It's relatively easy, but if you have two devices, it's not that straightforward yet. So to summarize, I believe that the integration PyTest with Twister opened really new levels of testing that was not possible before. I hope it can have a pretty low entry level. There are tons of tutorials on the PyTest itself. We also try to make the plugin very simplific for the end user. It also allows to like already pull many existing fixtures ready for you to use. You don't have to figure out how to configure your device, how to set up your serial, or should you use a fan in, fan out, or should you use serial connection. It's all there for you. So this is DUT type agnostic thanks to this device abstraction layer. Also, it's easily expandable. If you would like to add new type of device, then you can just either copy-paste the existing device and modify the methods which is using, or use this abstraction to get it there. And the same for fixtures. You can have fixtures in tree, you can have fixtures in your user module, or even if you're just downstream application. And the fixture itself, they are really scalable, so they can do really small stuff, like provide just a string into your test, but also quite complex things like setting the whole server and the whole network. They are highly configurable. They are also modular because, as you see, they are all sitting on top of each other. And they are also very reusable because every single test I showed to you, or it's using like a shell fixture is using duty fixture, and so on. So this is also an easy way to give you building blocks to play with in your test. And they also are quite nice if you want to do a setup and tear down. Unluckily, you didn't see the output, but it nicely points to you that this fixture was used on top of each other, all the stuff that they're doing. Now you're within a test, and now the test ended, and this is like a tear down procedure. So it's like winding and unwinding in a certain order. And just at the end, some helpful links. And that will be it. Thank you for your time, and I hope you have some questions for me.
Hello.
Have you ever used or do you envision using this test framework for reliability testing? Let's say you have a new hardware version or a new firmware version, you wanna stress test it, like test all the interfaces at the same time, reboot it like 1,000 times, like power cycle, see if it's gonna survive, like longevity testing, reliability testing. Is that a good framework for that, or is that different use case?
No, I believe it can be a good framework for it, certainly. I mean, I haven't done it. There are no tests like this, but yes, certainly. You just, because it's really up to what you can easily script in Python. Like here with this fixture, like if you look at maybe the shell example or downgrade prevention, with this feature you already get with the device which is pre-flashed for you. But maybe you want to go to the lower layer, which you can do actually, like doing disconnect and connect. Maybe you just can do a loop. I don't know, connect, disconnect to your device multiple times until you get an error. Or here in this shell test, maybe if you want to stress your shell, you can just make a loop over the shell execute command and I don't know, looping 10,000 times or looping for an hour, putting the information then and out and think if it's gonna fail or not. So certainly you can quite easily, also thanks to the Python, you can quite easily script all different types of testing. Thank you.
Have you experimented with using this with like a native sim test running within the PC? And if so, when you were receiving serial console traffic, could that also be tied into the dummy shell backend?
Most likely, yes. I haven't played with it, but surely, because like here, if you have this shell fixture, that particular one will use your device, and device is using this device adapter. But you can exchange like these pieces somewhere along the line, and instead of like using the real shell, you can, I guess what you're asking, you can do like some mock or some stub for your shell interface that it will be in a loop. So even like if you want to do this adapter, like here, so I guess instead of writing to real fun in fire out, maybe you would like to replace it with some dummy function that will provide the functionality you're looking for? Is it what you're asking?
Yeah, so I'll wait for the microphone again. In the native sim test with the Zephyr shell backend, it's possible to basically inject text into the console, then read information back out from it. There's a sort of a glue interface for doing that that's provided. I think being able to hook that into this would be pretty valuable because it's much easier to do regex and text-based parsing validation in Python.
Yeah, definitely. I'm quite sure that it should be done. I won't answer you to exactly how it can be done, but afterwards we can discuss, and I'm pretty sure it can easily be done. And yeah, regexes are quite nice in Python. My colleagues often, you can use the existing methods, but you can also use your own one. Like you see in that example, they like just write the method over using the like match no line or match lines, right? So to give you some user-friendly interface for this.
Yeah, I'll try to look into it because it could be pretty powerful. Thank you.
Yeah, great.
So to speak to the earlier question about stress testing, we don't use PyTest, but we use another Python test framework, Behave. But we do a substantial amount of stress testing on our hardware using very similar techniques. And then as far as to the talk, I think it's great that more people are trying to make hardware testing and firmware testing more and more approachable and easier, lower the barrier to entry. So thanks.
Yeah, thank you for your comment. And also maybe to comment back what you said, that yeah, often people already have solutions for this. And like internally, we have a huge amount of like proprietary testing tools. So those kind of tests were doing already proprietary. Like we have a means to do a Bluetooth connection and test it. But what we are really interested in to provide a tool that it's rather lightweighted, that first of all, it's like tuned to work the best with Twister, and which is also like open source, because I believe this is the greatest value if the users actually can start writing their tests, they can actually start executing their tests on their setups, and it's not like the company have the way to test the Bluetooth, but it's actually like the part of the native framework which is using the open source. So that was our main motivation here. Thanks for your comment.
For the lightweight M&M sample and test you showed, is that starting up a local server?
Yes.
So is this test using like a local Ethernet device? And do you have a solution if you wanted to test with a cellular device that's on the internet?
So first of all, I won't be able to answer all the details. I'm not very familiar with this, but I think they have quite a nice description of what's going on if you go there first. You can also contact the developer like Seppo Takalo. I'm sure he will be happy to answer. But then going further, basically what I wanted to stress during the presentation that you can kind of exchange these pieces. So right now it's using this virtual network and the protocols here. But nothing stands there. You can, instead of this, when you configure this virtual server, maybe you would like to use actually the real one that can do the stuff for you. And then instead of using this, this virtual connection, use the, like you asked for, cellular. Okay, yeah, the one. So yeah, and also like for, and this is running on QEMU or native POSIX. But it should be also quite straightforward to, I mean the same test should run with hardware. If you do the proper setup, the test doesn't have to change at all.
Thank you.
Actually, following on this line of questions, so if we wanted to run this on hardware, essentially, then the DUT would be the same because the device adapter hides those details, correct?
Yes.
But the lesson in that case, probably we will need to tweak it so that you'd have another version. And then if you want to go over the internet, of course, I'm assuming, like you said, that the setup and teardown methods where I can, like in here, for example, I'm assuming you're spinning up the Docker image and
so the Docker image is spun by the user before the test.
Okay.
And I believe it just gives you like the server running in that you can communicate. Right. It's open the ports and you can talk with the server.
Yeah, but there's nothing preventing you from doing that from Python as well. If you okay. Right.
I mean, yeah, you can just add a script that will start the Docker server and everything for you. Yeah.
And do you have entry points for like test suites in the sense that, for example, such an initialization routine, then it will only be executed once for all LWMTM tests?
Yes, this is actually, maybe I forgot to talk about it, but yeah, this is the great point. So this is particularly because this is also like an interesting story. Like Seppo was one of our, let's say, first customer, and we use this type of a test as a user story to kind of figure it out what would be interesting for the community and what kind of test they would like to do, what kind of functionality they would do. And in like the early version, we stick with this principle of having the test living in isolation and having the setup and tear down every time. But obviously, he started asking like, okay, I don't want to start my server every time. Right. I just want to start it once. And the same, I don't want to flash my device all the time. I just want to just reset it. And yeah, definitely there is a way to it. Like in your YAML file, I don't have it in the slide, but basically if you have like this section where you have this harness configuration, you can add extra parameters, like you can add PyTest root. But I think it was also shown in the here. You can have you can have a DUT scope in your YAML, and that it will tell you, in DUT scope in particular, it will tell you like, do you need to set up your DUT only once before the all test session or for each test session, like, and it's functioned by default, so one test, but it can be the whole session. Okay. So this is what I meant, that these fixtures can be nicely configurable, and they have a nice scope. You can define if it's only for very short amount of time to live, or if you're gonna to live for the whole session.
Yep, thank you. That answers the question. And then the final question, just to be clear, that if I understood the sequencing, so Twister DOS runs as usual, and
Yes.
it's just at the end that that PyTest is executed. And because what confused me is that is PyTest test no, then you flash. So when is it flashed for PyTest then?
PyTest is doing flashing.
Oh, PyTest is doing the flashing.
Yes.
Oh, okay,
So basically we have to like step out of the twister because also what we also realized during our tests, like especially like with this MCU manager, this was another example why we really wanted to have PyTest there, that we would like to do more stuff. We don't want to be flashed once and forget about it and just read at the end. Maybe we want to reflash or do reset to see if you're going to update or not. That's why we added a bit more functionality to the device side. So if you
so in the MCU Manager one, you had I think reset, but maybe not flash in the code. Reset device.
So it's reset, yeah. So in this example, the device will come firstly flash already because this is like the default what the Doot setup is doing for you. But then we are using MCU Manager to send the update to the image.
Okay.
But yeah, certainly you can do a bit more with it.
Thank you.
I think we have time for one last question here.
I'll be quick. Is there a convenient out-of-tree way to extend the device adapter factory, or is that what's the expectation there? If you have a custom simulation platform, you want to create a class for
this
that?
is, and we will be really glad. We will be really happy to support you if you want to add something. We hope we made it in a way that it should be really easy to extend. Like we try to do the abstraction, so at the base level you have this device abstraction, but then on top of it you have like the binary adapter, and on top of it you have like native SIM or QEMU, because depending what stuff are common, so what is common is on the lower level, and only the stuff which has to be replaced are on the top level. So I believe if you want to use your own, I don't know, like instead of calling a certain executable, you would like to call different executable, or instead of using FIFO file for communication, you would like to, I don't know, use something else. And I think as long as you follow these abstract methods that are required to have, then it will work. Of course, you can, maybe you will need to like stop the method, and because flashing doesn't make much sense in the terms of QEMU.
Yeah.
But maybe it's replaced with starting the emulator. But from the top level, they should look aligned.
Yeah, sorry, my question is more about injecting that new, injecting the constructor into the factory so that the fixture is generating the instantiation of your unique device adapter subclass,
yes.
right?
Yes, I believe it should be easy.
Okay, we could chat after.
Yes.
Great. Thank you. That concludes this session.
Thank you.
Hello everyone, am I audible? Okay. Hello everyone, good evening. Thank you for joining with me. I am Vaishnav Achat from Texas Instruments, and today I would like to talk to you about a proposal for a remote processor framework in Zephyr RTOS. I work with the Linux team at Texas Instruments and primarily working on Linux and U-boot for TI processors. TI is a part of multiple open source organizations, including Zephyr RTOS, and we focus on upstream and open source ecosystem in our device definition phase itself. So as part of my day job, I work primarily with Linux and U-boot on TI devices. I am also the maintainer for TI platforms in Zephyr RTOS. So here are a few disclaimers. So this is just a work in progress proposal and get the community feedback on the proposal for a remote processor framework, why we thought we need a framework in Zephyr RTOS. And this is not a complete implementation, and we'll be working on a RFC and the standard process for introducing the subsystem once we gain sufficient feedback from the community. Okay, this is how the talk is being spread out. So first we'll go through what is remote processors, then the motivation of why it might be useful to have a remote processor subsystem in Zephyr RTOS, and we'll also discuss on existing ways of managing remote processors in Linux and U-boot, and how that does not cover all the system level use cases. Then we can discuss on how we can introduce a remote processor framework in Zephyr, both in client and also in host mode, which we'll discuss in detail and more. And also we'll have the benefits of having something like this and future plans, what we are working towards. Okay, what is a remote processor? So unlike traditional microcontrollers and microprocessors, where there was a single CPU core or multiple CPU cores of the same type working in SMP or symmetric multiprocessing mode, today's processors are very complex and have a heterogeneous architecture with the same SoC, having multiple application cores, multiple real-time MCU cores, then multiple low-power MCU cores, and sometimes system controller cores, DSPs, and so on. So remote processors are those processors in the system which is managed by the host. So it's we kind of think like it's always the application processor or the biggest processor in the system as the host. It's not necessarily true that the biggest processor, maybe the application processor running Linux, is always the host. So for example, if you take the case of a bootloader, which boots up multiple cores in an AMP system, so you can think of the bootloader as a host which boots up all these remote processors, others. So let's say in case of our devices, we have a startup core, a Cortex R5, which boots up the Cortex A53 or A72 cores. So in that case, we can think of that Cortex A core as a remote core with respect to the bootloader. When you come to Linux and you work with like maybe you have a DSP accelerator core, or you have a real-time MCU core, then those cores which you manage from Linux are the remote cores when you look from that perspective. And today there is a very mature framework in Linux and U-boot for the management of remote processor cores. So from Linux or U-boot, you can start, stop, load the firmware, shut down, or even attach to a running cores and do all those kind of functionalities. And Linux also has some advanced features, like you can start a communication channel through the standard RP message framework, and also do some advanced features through the RP Vertio drivers. So for the discussion, in this discussion, we'll be having some implementations or demos. So we have taken a TI AM62 platform as a reference, and this has a application processor Cortex A50, quad-core Cortex A53, and a remote MCU, a Cortex M4F. So traditionally, we use systems where we just boot up the M4 from U-boot or from Linux. But in the end of the system, you will see how we have able to get both of these cores running Zephyr, and how we boot up the boot and load the remote processor from Zephyr. So you might have a doubt, why even use Zephyr on application processors? So those are designed with an MMU and the complex pipeline to run Linux or a high-level OS. And while in most cases Linux is the popular choice for running on application processor due to the versatility, Zephyr Autos can also be a good choice you can run on the application core, because Zephyr supports SMB symmetric multiprocessing support on Cortex-A, the 64-bit ARM cores, then gives you real-time performance. Then there are complex subsystems like networking, graphics subsystem, display, USB, everything, which you might not get from some of the traditional RTOS, where you might not even have a device driver model and all. Then Zephyr also have some features like power management, which might be suitable for. So it's kind of sits in a sweet spot where you don't want the complexity of Linux, but you want a lot of features that Linux also offers. And also it's much simpler to configure and develop than Linux, and you have a much smaller application size. So most of the times everyone prefers to run Linux on a high-level OS and on the application cores. But on some systems, you might need deterministic behavior or real-time behavior, and you need to switch to the preempt RT or the real-time Linux kernel. The real-time Linux provides the versatility and rich ecosystem that Linux provides, along with the real-time deterministic behavior. But Linux and real-time Linux are much more complex, and you have multiple tuning knobs that you need to configure properly for your system to get the actual deterministic performance. Zephyr is much simpler, and even though it's not as versatile as Linux, it provides a necessary subsystem like we discussed to implement complex use cases like networking, graphics, display, USB, and all. And also, if you look at Linux or real-time Linux, the device drivers that's being used in real-time Linux is the exactly same as what you have for the vanilla Linux. So you might not have thought of a proper real-time implementation for your device drivers. So even though you adjust all the tuning knobs for real-time Linux and perform all the optimizations, if you have not implemented the device drivers properly in Linux, you won't get the deterministic performance. But if you look at Zephyr, you will have the mindset that it's an RTOS and you are implementing the device driver to behave in a deterministic manner. So we have had previous debugs and issues where we did not get the proper real-time deterministic performance from the device driver. So the kernel, the scheduler, everything provides you the real-time performance. Sometimes you might not get the determinism from the device drivers because you did not implement the device drivers for a real-time system. You just implemented for the normal Linux. But that's not the case with Zephyr, but you develop with an RTOS mindset, and from the day one you will be implementing that in a way that you have the real-time performance for the device drivers. And now, so that why Zephyr can also be used in application cores. Now, why even have a remote processor subsystem in Zephyr? Why not boot up all the remote cores from bootloader? So we saw that U-boot supports. So why not boot up all the DSPs and all the remote cores from bootloader and just forget about it? So that's where, U-boot has a very good subsystem where you can load the remote cores, even boot up Linux, the DSPs, everything. But for some use cases, you cannot just have the remote cores booted up initially and just forget about it. For example, you want to do power management. So the system is choose to suspend when there is no activity. And when it resumes, you need to resume the remote processes also. But consider the case where you don't have Linux in the scenario. So you have Zephyr running on your complete system, Zephyr running on the host processor, and Zephyr running on Zephyr or maybe another RTOS running on your remote processors. Then what happens is when you resume, you don't have a proper management framework to start up these remote cores and load the firmwares. But maybe just do a plain startup from U-boot, you have the necessary framework over there. And power management is very important feature that you will need to implement in most of the production use cases. And in this case, if the Linux was the host operating system, then you can have there is already a mature remote proc subsystem, and during resume, you can choose to reinitialize and reload the firmware and start up the remote cores. So coming to the motivation, so we always see Linux or real-time Linux in use cases. So we are looking at a hypothetical use case where we have application core running Zephyr, and you have a high-resolution display with multi-point touch, which needs to provide a rich HMI interface. Then you can have networking and communication protocols like Ethernet and CAN, and then you can have separate remote processor cores running Zephyr, doing some real-time tasks like motor control. You can have DSPs running workloads, so you can capture images on maybe a factory line and do analysis on a conveyor and do things like that. So traditionally, due to this, since something like a remote processor subsystem is not available, you can maybe do some of the features and implement this with Zephyr, but even though Zephyr provides the subsystem, we find some difficulties in getting these implemented. And also, Zephyr has a very rich networking and the communication protocol stack, and we get the sweet spot between Linux and the traditional RTOS, where you don't have those rich frameworks, but you don't need to go to Linux for the complexity. So now we kind of understand why, or the motivation behind why we need the remote processor subsystem. So let's take a look at the Linux remote processor subsystem to gain some inspiration and how we can take the implementation as a reference. So Linux has a very mature remote processor framework starting maybe 10, 15 years ago, and it's a host implementation which allows you to power on, load firmware, stop the remote processors. And the framework is there so that you can abstract the hardware level differences. So one hardware, the SoC vendors' way of starting the remote processors might not be the same for the other SoC vendor. So you need to abstract away and give the common helper functions which the different SoC vendors can implement in their particular drivers. And in addition, the Linux remote proc framework is very complex and has some very complex features like the RP message Vertio devices, where you have a standard transport and platform-specific remote proc drivers only need to provide some low-level handlers, and the RP message drivers will just work. So for example, there are things like RP message, TTY, and all, like, which gives you an RP message UART over the RP message transport. So it will just work if you have the proper entries and handlers in your firmware. You don't need to do any plumbing in the Linux kernel to get this working. So you just need to advertise in your firmware. So the subsystem is just split into, so there are core functionalities like starting, stopping, and preparing the processor. So we'll discuss on each of these functions in detail so that we can take inspiration from this and implement similar ones in Zephyr. And there is also an ELF loader, so we need a cross-architecture ELF loader. So in these heterogeneous systems, you have maybe one of the cores as the host, and the other cores where you need to load the firmware might not be of the same architecture. It might be a different architecture. So there are Vertio helpers and the character device implementation. Those we won't go into deep because that's not relevant to if we want to implement it in Zephyr. So what's the minimum thing that you need to have in your remote processor client firmware to have it loaded and processed by a remote processor host? So the standards are governed by the OpenAMP project, and there is something important called the resource table that the client firmware needs to advertise or provide it in the ELF binary. So the client firmware needs to have a section called resource table in the predetermined format, which that standard is governed by OpenAMP. And so this is how the resource table looks like. So the resource table has a header where we have fields like the version and the number of resource entries. And each resource entry is also a structure where you have each resource entry has a header which determines the type, and depending on the type, it might have the contents. So what are resource entries? So resource entries are sometimes just telling the host that, okay, we have these capabilities. Sometimes we want to negotiate and get something from the host. For example, if you just start up a remote processor client firmware, you need to sometimes ask for some carve-out regions in the DDR, which the host is managing. The host can allocate this region for this particular remote processor and share the address and the size of the region as a response. So the client advertises or asks what it needs through the resource table structure, and this is how it's laid out. We have a common resource table header, and each entry has a header which has its type and data, and depending on the type, we are parsing the contents of the resource table. Now we are going to look at what are all the operations or the API that the remote processor subsystem in Linux implements. So first one is the remote processor operation prepare. So you need to load firmware and start a processor to run. But to load firmware on a processor, you might need to maybe do some initialization before even starting to load. Think of it as switching on the processor. So if you have a heterogeneous processor and the remote core might have SRAMs or TCMs or local memories that you need to power on this, and also to avoid leakage, you don't power on anything in a multi-core SoC if you're not using it. So you need to power on this core and those regions that you need to load the firmware first before loading the firmware. So this is kind of a step as a prerequisite before loading the firmware. So this will be called before loading the firmware and before starting to run the code. So this is how you implement it. So sometimes you might even need to just set the TCM or SRAM to 0. You need to do a mem set and clear the stray values in the memory. So that's what the prepare function does. So now one of the most complex functions is the load function. So you have a ELF binary that you need to load, and the ELF will have different sections that you need to load to different parts of the memory. Sometimes these sections could be in the DDR. Sometimes it could be in the TCM or the internal SRAM or the IRAM, and it could be different sections. The complexity arises when you are loading it from a different processor, and both of the processors might not have a same view of your system. So if you look at a standard ELF loader, you just read this section headers, ELF header and section headers, pass through the section, and just do a mem copy and load it. But if you want to load to a remote processor of a completely different architecture, and it might have a different view of the complete SoC memory map. So the address 8000, what the host sees might not be same as what maybe it might be the address 0 for the remote core. So that's where you need to have a custom implementation of something called DA to VA. So that's the device address to kernel virtual address. Take for an example, your device, the remote core has an TCM or SRAM, which has the address 0 for an example. Now, if you look from a host, which is another processor, your SoC will have a TRM where you will see the memory map. So this TCM or SRAM might have a different address when the other host client processor sees. So the DA to VA is the mapping that you provides to map from the host's view from the device view, because the ELF sections will have the device view implemented in there. And then also there will be DDR sections. You might need to load it in the DDR section so that you just map and return the address. So you looked at load, and load had a dependency. You need to have a translation. Now you have loaded the firmware in the expected regions that the core expects. Now you just need to start the processor. Now this also is it's very specific to your the vendor's implementation of the process. Sometimes it's just releasing the reset. Now if you go into deep how the releasing of reset, some devices, it might be writing to a register to release the reset. Sometimes heterogeneous processors have a system controller which manages all these things, and you send a message to the system controller, and that does release of the reset. So that a central entity controls the power, turning off the power and reset of the entities in the SoC. So you do your SoC specific, the core specific implementation in your start function. Now you have started up the core, and you need to stop the core. So here also your SoC will have specific implementations where you need to follow. So let's say I was talking only about the remote cores being a single core. Sometimes it can be a cluster of multiple cores, and you might need to do some sequencing when you need to power off or releasing the processor. So you implement all this in this function. And now we are coming in a symmetric manner. We prepared, we started, we load the firmware, start, then we stop, and unprepare is just a symmetric version of prepare, where you release the resources and power down the processor. So now we have discussed on how the host implementation of remote processor is in Linux. But Linux cannot ever be a remote processor client. Usually it's always only the host that manages the other remote processors. But if you look at Zephyr, it runs on Cortex big application cores to smaller Cortex M microcontroller cores. So it can be both a host and a client. So we are just discussing about the client interface. Zephyr already supports this, so we can have the firmware compiled with resource table and load it to a remote processor. It's all using the helpers from the OpenARM library. There are already implementations, so there are platforms reusing it, and one of the platforms I took for the demo is also implementing something like this. But we are, since we don't have a framework, we are duplicating some of the code, and each platform is implementing on their own implementation. For example, I just did a grep of resource table, how different platforms are packing the resource table to their images. So if you look at 7 or 8 platforms there, they're all packing the resource table and having their own implementation, where the resource table is a standard entity that's governed by the OpenARM standards, and you don't need any specific implementation for your platform. So you could just have a common linker include and things like that to make this process efficient. Zephyr already supports the client mode, but we want to have some advanced features. So you have, we discussed about the system suspending. So you cannot sometimes abruptly stop a running remote core. So the remote core might be holding resources on your heterogeneous system, and if before you stop the core, you need to have some negotiation and let the remote core properly release all the resources it has requested, and then properly do a shutdown. That's called the graceful shutdown feature, which we have to implement on not on Zephyr, on one of the other RTOSs for our customers and in our SDKs. But if we had a standard framework, we could use that framework to combine with the device driver model in Zephyr and do a cleanup before doing a shutdown. So Zephyr, since it has a device driver model, it's very easy to hook something like this to the existing helpers in Zephyr. And also now, even though there are some implementations using Zephyr as a remote processor client, we need to have some implementations where, so we discussed the resource table. So the client can request resources and entities from the host and get those as a response and do the implementation. We have some implementation like RPA, remote proc TTY and all, but we could improve that implementations to have advanced features like memory carve-outs, which is very important when you are working with DSPs. So you need to have memory carve-outs to do the processing and do the inter-processor communication. So right now what we are doing is a static allocation. We have a static, we carve out memories, we are statically allocating. We are not negotiating with the host. Now the host can be Linux or Zephyr, but in Linux also the host has the ability to do something like that, and Zephyr also can do that, but we don't have a common reference or example, or the framework does not support it. So now we looked at the host and client implementation. So I have tried to implement something like a remote processor host implementation. So this will just expose some API functions. So we discussed on how it was implemented in Linux. So again, this is not the version I might be putting in the pull request, so we are just looking to get feedback and get to some proof of concept that's working. So we are just implementing the host implementation where you have prepare, unprepare, then the start, the load, and the device address to virtual address conversion. So if you look at prepare, so I'm taking a TI processor as an example. So I'm taking the A53 application cluster running Zephyr in SMP mode as an example as the host, and the M4 MCU as a client. So for prepare, so this device has something called a central system controller, to which you send messages to tell you need to turn on this power domain. So you don't have your host going and writing registers to power on or power on things. You just send messages to the common entity so that you have a common entity that manages all the resources, power, clocks, everything in the system. So that's what, so if you look at prepare, what I'm doing is I'm turning on the device power domain because I need to write to the internal SRAMs of the core. And also I am holding the device in reset so that whenever I load the firmware, I don't want it to be in a running state. And in start, what I'm doing is I'm just sending the message to the system controller to release the device from reset. And in unprepare, we are just going the reverse. We are turning off the device. Now coming to the complex part of the ELF loader. So I was looking at how we can process ELFs in Zephyr. So I looked at it and I saw that there was already an implementation using the LLEXT implementation where they're already using the ELF headers, and there are some helpers that we can reuse. So there is also another place where you have ELF helpers in Zephyr, that's from the OpenAmp library. So I'm not using it from the OpenAmp library now. I'm using the in-tree, the LLEXT version. So if you look at how the ELF loader is implemented, I'm not sure if it's visible. So if you just do a sanity check of the ELF and you iterate through the sections and you try to memcopy and load the different sections of the image. And sometimes you might also need to clear the some of the sections that are not filled, does not have full contents. Now, when you want to load it, you need to have a device address to virtual address translation because your host's view of the system memory might not be what is in your client's or the remote course view, which is what the ELF is having. So this is the implementation I have now. So just summarizing, we have the remote host, which allows you to boot and interact with other cores running firmware with a resource table. And host support is exactly similar to what you see in Linux or U-boot. Linux has a much advanced implementation, but we are just focusing on just booting up the cores and stopping the cores. And client mode, there is already supports, but we think we can improve using the helpers provided by the OpenAmp libraries to have more things like the negotiating for carve-out memories, doing graceful shutdowns and things like that. And also the client firm, we saw that every platform is just duplicating the linger commands. We could have had a common linger command. So things like that is what we wanted to optimize using the client framework. So now coming back to, we discussed some why the motivation behind introducing the framework in Zephyr. So MCU boot has a Zephyr port, and it could, if we have a remote processor framework, it can reuse the same drivers, and you can have it as a standard open source, very lightweight bootloader for AMP systems. So if you look at some of the TI SDK offerings, we have some RTOS-based bootloaders where it's not based on Zephyr unfortunately, but it can even boot up all the remote cores, and it can even boot up Linux running on an application core. So there is actual need for a lightweight bootloader which can do a very fast startup. U-boot has a lot of sequential phases which steals a lot of your boot time, which sometimes you cannot afford on some of the production systems. And also, like in introducing the framework is not to duplicate the host and client mode implementation, so that each vendor can add their own implementation without duplicating it. And also, we can enable applications with different kinds of cores working together and running Zephyr at the same time. Before it was just Linux and Zephyr running on some of the cores. Maybe we can even have Zephyr running on all of the cores. So I have some demo. I have running on M62X EVM. So we told that it has an application processor A53 cluster and also a M4 MCU clusters. So today what we can do is we can load firmware on it from the remote core from U-boot. So I'll just show what we are doing from U-boot. I'm hoping it's visible. So we are at the U-boot A53 console. And what I'm going to do is I'm going to fetch the remote processor binary. So I'll be running Zephyr on the left side. That's the A53 application processor console, and on the right side, the console is empty. It's the console from the M4 MCU cores. So I'm fetching the binaries from over the network. So I'm just doing, so U-boot has a command line interface where you can do help some remote processor functions. So I'm just listing down, and it listed that there is an M4 MCU application, MCU core. So I just, so we looked at the sequence of functions. So we stopped the core. So we prepared it for loading. We fetched the image, and we are fetching two images. The first image is for running on the M4 core. The second one is for running on the A53 core. So I'm starting the remote core. You can see that the Hello World application with the console shell access has booted up on the right side console, which is the M4 MCU core. And on the left side, you can see that Zephyr is running on the A53 application core as well. So this is what we can do today with Linux, U-boot. So now let's look at I showed you how the API for Zephyr was implemented, and we'll look at how the same thing happens. So right now what I'm doing is I won't be running any remote pro commands from U-boot. I'll be just fetching the firmwares and just using the remote pro commands to boot Zephyr on the A53 application core. The Zephyr application on the A53 core will read the binary and go and load the M4. So I am just fetching the binaries. So we need to get two binaries because for first one we are running on the application A53 core, and the other one you are running on the M4 core. So earlier I had run, so you can see how fast that the M4 core start up from the applications, because you are not booting sequentially from the U-boot, but we are starting it from Zephyr. So the Zephyr has booted up from the core. So I have some debug logs. So first thing we are doing in this application is, I told you there is a system controller that we need to negotiate with to do resets, powers and all. So first we are talking with the system controller and printing out the version. Then we are requesting the processor handle, powering up the processor and putting it to reset, then do the ELF loader, load the ELF sections, and then release the processor from reset, and the example runs on the M4. So coming to the open items and future plans, so this is just a proof of concept we have, and we'll be working on an RFC pull request and describing on what the benefits are, and we need to add test cases, and we need to do it present in the development review for getting a new subsystem. And we are also exploring on how we can optimize and improve the client implementation to do things like graceful shutdown and resource requesting and negotiating resource to the host. And also what we would like to really explore is how can we have MCU boot as a standard, very light bootloader for a complex heterogeneous system like those devices you saw before. And now I'm using the ELF helpers from the LLEXT implementation. So I talked with a few people from the OpenAMP, and they told that there are already implementations and ELF helpers there. So we'll be exploring if we can reuse them as well. So now the ELF loader was written from scratch, taking inspiration from the implementation Linux. So most of the implementation we took from was Linux, and the OpenAMP is the governing project that provides the guidelines for the remote processor framework and all. So we got into the discussion of this framework when we tried to add support for one of the platforms, and we were reproducing existing linker commands and code, and that Carlo was the person who suggested if it might help if we have something like this. So these are my contact details, and I'm available for any questions if you have.
So if I got this correct, you start the first Zephyr.
Yeah.
And then second Zephyr has, the first Zephyr has this application that starts the second one.
Correct, yes, correct.
And how does first Zephyr knows where's the image for the second
So
one?
right now I am just hard coding those, so we can have it help us to read it from Flash, or we can have it in device tree. Usually in a bootloader's perspective, it will be in the boot medium, maybe an SD card or Flash memory.
Okay.
So in this implementation, what I'm doing is I'm loading it to the DDR from U-boot, and I'm just reading it in my application.
Very good talk.
Yeah, thank you.
So I believe on these processors, TI has some clocking firmware that needs to run. I'm not sure what the name is, right? But there's something you need to do to be able to service the clock tree structure to turn clocks on and off. So is that an object file that you're linking into the Zephyr image, or does that exist somewhere else when you're running on the M4?
So when we go and do the MCU boot path, where we want to have the MCU boot as a bootloader, at that time we'll need to think about loading this firmware. So what I'm doing is I'm starting from the U-boot console, where all of these the device manager firmware, the security firmware is already loaded. So when we want to have the MCU boot as a bootloader, we need to have a way to have slots and load all these firmwares to the remote processors. So again, how U-boot does is also through the remote process framework. So if you look at the system controller or the security controller, the firmware is usually loaded by the ROM, and the power management, the clock management, the device manager firmware is loaded from the U-boot. And on these devices, it's a Cortex R5 core, and that's also being loaded through the remote processor framework in U-boot. So if you have a framework in Zephyr, so you can either pack the binaries like U-boot does, or maybe have slots in additional slots in the MCU boot, the flash layout, and pick the firmware from there. We have not explored something like that, but if you need to have a standalone bootloader, we need to do something like that. Since I used U-boot, all of those are loaded by U-boot already.
Do you have a real use case in mind with that, or just exploring for now?
So we are exploring. So we have real use cases in our SDKs with the different RTOS. So we are trying to achieve something similar here.
Okay.
Any other questions?
Okay. Thank you. Thank you everyone for joining.
All right. Is this on? Can you hear me good? All right, cool. Let's go ahead and jump into it. Thanks for sticking around for the last talk of the conference. You never know what the turnout's going to be like, so I appreciate it. My name is Dan Mangum. I work at a company called Goliath. We make an IoT platform, and today I'm going to be talking about WebAssembly on Zephyr. But the talk is pretty expansive, so I'm going to be moving pretty quickly. We're going to start off with talking about just what WebAssembly is and how it works. Then we're going to move into kind of talking about dynamic code execution in general, when you should do it, when you shouldn't do it, what some of the alternatives are, and then round out with actually looking at a demo of running WebAssembly on Zephyr and talk about what some of the attributes of that are. So let's go ahead and jump in to kind of an introduction here with how WebAssembly works. So effectively, in any environment where you're going to be running WebAssembly, you start out with what the spec refers to as an embedder. This is basically the host environment in which a WebAssembly module or multiple WebAssembly modules are going to run. For an embedder, in order to run a WebAssembly module, you need to get a binary representation of that WebAssembly module. That could be, anything from on disk to fetched over the network. We're going to be talking about a variety of different models for accessing WebAssembly modules today. So once you get that WebAssembly module, you go through a number of steps in order to actually invoke code that is in that WebAssembly module. So those steps are broadly going through decoding, validation, and execution. And these are all core parts of what makes WebAssembly useful in some cases. So looking at decoding, this is runtime defined. So depending on what WebAssembly runtime you're actually using, the representation of a module instance, which is what we're moving towards here, is defined by the runtime, so it may look different. Frequently, it's represented as some sort of abstract syntax tree, but it doesn't necessarily have to be, and especially in more constrained environments, there may be other ways to represent it that can help with code size and things like that. Then you go through a set of validation. So you're basically taking that representation, running it through a number of specs, a number of attributes in the spec that classify it as well-defined and ensuring that it is a valid WebAssembly module. And then you move into execution. And execution is really what we care about, right? We want some functionality out of this WebAssembly module. So there's two steps to execution. You start off with instantiation and then invocation. Instantiation is exactly what it sounds like. You need to provide definitions for imports, so things that the WebAssembly module are going to access that are provided by the embedder or the host environment. You need to initialize globals and memories and things like that. And then if the WebAssembly module has a start function, just like any executable, that is typically run during instantiation. Now there is some variability between WebAssembly runtimes as to whether that happens, which a lot of times is revolving around security, whether you want to go ahead and execute a function when you're instantiating or you want to wait for invocation. So if there's a start function, that's the time in which it runs. And then in invocation, you're basically pulling an exported function out of that WebAssembly module, and you're invoking it from the host environment. And you may pass it some arguments. And if you're going to pass it arguments or receive arguments from it, the runtime needs to validate that those arguments are valid. So it validates the number of arguments you have, the types of the arguments. And WebAssembly is a stack machine, so those get passed by putting those on the stack for the WebAssembly module instance, then invoking the exported function, and then it will push the return values onto the stack, which then you can pop off to get values out. Okay, so what is in this module that we're creating an instance of, and how are we able to kind of like communicate across boundaries from the host environment and the module instance? A WebAssembly module looks a lot like any other executable file in that it's made up of sections. There are a lot of sections here, and there's a lot of different things you can do with WebAssembly modules, which are one of the ways that allow it to be so portable. We're not going to go through all of these today. I did write a blog post if you're interested in understanding every byte in a WASM module. You can go check that out if you have 21 minutes on your hand to look at a lot of hex dumps. But we're going to talk about 3 specific sections today because they're kind of relevant for how we're going to interact with a WebAssembly module. So let's start off with an example module. One of the things that's going to be kind of a common theme throughout this presentation is that a WASM module WASM can be targeted by really any language. So we're going to be using Rust as an example today, but you can obviously use other languages as well. This is a very simple module. What we're looking at here is that we have a single function defined in the WASM module. That is maybe alert. It takes a value. It compares the value to a constant value, and if it's over that value, then it's going to trigger an alert function, which is provided by the host environment. And so you can see that we're declaring the alert function, which does not take any arguments or return any values. Once again, a very simple module here, and that's going to be provided by the embedder. Typically, when we look at a compiled WASM module and we want to see what's inside of it, we'll represent it with WAT, which is the WebAssembly text representation. And so you can see some of our function body being translated to WebAssembly here, as well as things like the exports and imports and various signatures for the functions. So starting off, if we look down towards the bottom of our WebAssembly module here, we have a custom section. The custom section can provide really anything. It's runtime defined or compiler defined in this case. And so here we're just saying that this was compiled by Rust-C and the language is Rust, but it can also provide third-party extensions. One of the things that's really important when working with WebAssembly on microcontrollers is the amount of memory we're going to use. And it takes memory to be able to take this WebAssembly module, translate it and interpret it, and then execute it. There's obviously more overhead than just running native code would be. So for an example, some WebAssembly runtimes that can be run on microcontrollers will take the native code for whatever target is going to be targeted, or for multiple targets, shove that into the custom section and actually have it along with the WebAssembly module. So you could have it executed natively or interpreted depending on what environment you're in. So you preserve that portability while also improving performance in the more constrained environments. Looking at the import, that's exactly like we said. We have an alert function. You can import functions, tables, memories, globals, basically anything that you want the WebAssembly module to be able to access that's outside of its sandboxed environment. There is a namespacing mechanism for imports. So here you can see we're in the env namespace and we are importing a function with name alert. And the function imports, which is the only kind that we have here, are going to include a signature, which basically allows the WASM module to know how to, or the WASM function that calls it, know how to invoke that function. And these must be available at instantiation, which may be obvious because we mentioned that when you start or invoke the start function, you need to have access to all of the imports. We also have the exports. So we're exporting a variety of things by default, and then we explicitly mention that we would export that maybe alert function, which is going to make that available for the embedder host environment to be able to call. So once again, functions, tables, memories, globals can be exported. And it's not a 2-level namespace in export, so that was copied over. And these are available after instantiation. All right, so why do we care about these specific sections? Well, I already mentioned the custom section and how that can be useful for constrained environments. But for imports and exports, one of the important things to think about is if you're going to put something in a sandbox environment and get some of the benefits that come with that, you're going to need to be able to communicate outside of that sandbox environment to be able to do anything of consequence. So if we're going to share primitive values across a sandbox boundary, WASM only supports very primitive types. So basically integers and floats are what you're going to be able to pass as function arguments and return values, which significantly limits what you can do. So we're going to pass those primitive values as function arguments and return them as values. And if you're going to share complex values without any other mechanisms, typically what you would do is from the host environment, you're going to write into a section of the WASM module instance memory, and then you're going to pass an address to a function in the WASM module so it knows where to access that data in its memory space. But fortunately, lots of people have struggled with this, and it's not a great way to pass around more complex values. So there's kind of two components that are important to understand in the WebAssembly ecosystem. So the first one is WASI, or the WebAssembly System Interface. This is kind of like POSIX for WebAssembly. So you can see here the kind of summary of it, but basically it is a standard interface. So think about that alert function that we imported into the WebAssembly module. Imagine if you kind of had a set of libc functions that were basically available and you could count on those being present. That's kind of what WASI is defining for WebAssembly modules. And you'll see we get a nice call out of embedded devices in the high-level summary. The other part of that, which version 0.2 of the WebAssembly system interface is built on top of, is the component model. So you can imagine if we have lots of WebAssembly modules that are all importing and exporting different functions, it can be very hard for these to interoperate with each other. So the component module goes beyond kind of those primitive types in various different imports and exports and allows you to declare interfaces that then can be implemented essentially by various WASM modules. This allows you to also combine WebAssembly modules that are compiled from different languages and have different ABIs and that sort of thing to work together all at once. So WASI 0.2 is built on the component model. All right. So what we care about here, at least today, is WebAssembly on microcontrollers. For some background, WebAssembly, as is widely known, was primarily built to kind of replace JavaScript in a browser context, but it was an explicit goal for that to be able to run elsewhere and also be useful in those environments. So the WebAssembly specification mentions a variety of attributes or motivations for its design, and they fall into two categories: semantics and representation. So on the semantics side, we have a number. We're going to go through these individually, and we also have on the representation. But what we're kind of asking ourselves here is this better than the status quo, right? Like, why would we want to introduce more complexity into our firmware? And there's a variety of reasons we may want to do that, but it really comes down to two different categories when you're evaluating these various attributes and whether they would be useful to you. The first is you require dynamic code execution, so you have to be able to do this to accomplish a given use case. I would argue that that's probably less frequent than we might say it is that you need to do that, but there are definitely valid scenarios, but also evaluating it in the context of it not being required. I think that that significantly constrains the reason why you would want to put an interpreter in a sandbox environment onto a microcontroller, but there are some instances in which that can be useful depending on the rest of your system and what's surrounding that embedded device. So does your product require dynamic code execution? Like I said, probably not. So if you don't need to introduce more complexity, let's not add more complexity. Let's not use up more of your memory in your firmware. Carefully think about whether you want to do that. There's also alternatives if you do need dynamic code execution. So I went to a talk earlier today on Lex, and that is native to Zephyr now. And there's a lot of great capabilities there. There are some differences. I'm going to be talking more generally today, comparing kind of like against all alternatives vaguely. But if you want to get more into specifics, we can talk after, or the folks who work on that subsystem can certainly give more information than I can. All right, so starting off with some of the attributes of WebAssembly is that it strives to be fast. And so it tries to execute with near native code performance. Obviously, when you're interpreting, there is overhead compared to native code, but one of the ways that the that WASM is able to get closer to that is by modeling a lot of modern hardware function in the WebAssembly virtual ISA, if you will. So WASM strives to be as fast or faster than JavaScript, but a lot of times we're not comparing to running JavaScript when we're talking about microcontrollers. So is WASM going to be faster than C? Typically not, right? So if you don't need dynamic code execution, you're going to be giving up some performance likely. I will say this is less than or equal to because there are some caveats whenever you're doing JIT and being able to get more context when you're compiling on the fly. But if we're talking about whether you need dynamic code execution, is it faster? In both cases, if you need it or not, you're probably going to be giving up some performance here. So that's a kind of penalty you get for bringing WebAssembly into the picture. When we talk about safety, WebAssembly is very interested in safety because when you're executing code in the browser, you're primarily fetching untrusted code from all over the internet. So it's very important that you're able to sandbox that well. That may be less important on a microcontroller because you probably aren't running third-party untrusted code, but in some cases you may be. And in that case, that isolation is useful. So like I said, it's really valuable when you're running multiple untrusted programs. But there are also memory-safe alternatives to embedded C. So I know there's been a number of talks about Rust. That's not the only memory-safe option. There are other alternatives as well, but that's just one that's obviously been popular as of late. So if you need dynamic code execution, this isolation is going to be useful. If you don't need it, there are other ways to get memory safety and probably less complex ways as well. So grouping the next few together, well-defined, hardware independent, and language independent. If you're only going to be running code on a microcontroller, doesn't really matter too much if you're hardware and language independent. So this isn't bringing too much value for us. It is useful if you're going to be moving that between different environments or potentially onto different microcontrollers. But once again, embedded languages, if you're compiling firmware binaries, you can target different architectures. And obviously, if you have a system like Zephyr, it's really easy to move between different hardware. Another thing that's important to note is because we're still doing, we're executing in a linear memory space for a WASM module instance, languages that do not have direct memory access or can directly access hardware are still going to struggle in a context where that's necessary. So if we're passing pointers and offsets to functions, accessing that memory and working with it, even within a WASM module instance context, is going to be difficult with a language like JavaScript. So if dynamic code execution is not required, these are not super useful for you. They're also not necessarily super useful for you if you do need it. You can get some of these right with Lex or something like that. Platform independence is something that I think is a little more interesting to think about when you view a full context of a system of which an embedded device may be one component. Platform independence is a goal of WebAssembly, and at least at Goliath and in some of the work that I do, we think this is really interesting. So I would say the kind of killer application of WebAssembly in embedded is transferable computation. And when I'm talking about transferable computation, basically saying you can move operations between different types of heterogeneous compute depending on what your goals are and where you're trying to optimize. So this can be really useful for cases like you want to manipulate data at different points of the process of that data getting from an embedded device to ultimately being in a data store. It can be useful for making data-driven decisions, which is something we're going to be looking at a demo for today. And it can be useful when you're prototyping or experimenting. If you're going to have static behavior that's not changing that much, once again, having dynamic code execution is not going to be super useful to you. But in both these cases, platform independence can be useful. Open, I'm mostly going to skip over this. I'm going to assume here at the Zephyr Developer Summit that we're all interested in open and many alternatives are open. So we're not really getting too much of an advantage by WebAssembly being open, but it's great that it is. All right, looking at the representation, I'll move a little faster on this. A bunch of these are not taking into account the fact that you have to have a runtime present in the environment. So if you're in a browser, right, that's not too big of a deal. If you're on a microcontroller, that may be the most significant use of memory on your device. So that's obviously going to be an issue. Also, if you're just thinking about being able to minimize the size of the code that you're getting down on a device, there are other ways to do that, and they're going to pretty much always be more efficient than having an interpreter you need to put on the device and then fetching a module to run on that interpreter. And a lot of times raw speed is also not our most important attribute, and you may be willing to trade that off for things like conserving power or being able to go to sleep more often, that sort of thing. So once again, WebAssembly not giving us a lot of advantage there in a vacuum. But portability is kind of related to the platform independence. And so the portable representation that WebAssembly gives us is really, at least for today, with what we're concerned about, the most valuable attribute of WASM in this context. All right, so if we look at a system where we're using WebAssembly across heterogeneous compute, we think about that a lot at Goliath, and what that may look like is having a lot of devices on one side and then some type of middleware in the middle that is getting that data off the device into a cloud somewhere else or to a consumer application somewhere else. So we like to talk about the device side and the cloud side, and then having middleware in the middle where you can optimize that data, you can transform that data, and then you can ultimately deliver it to where you want to use it and consume it. And this is bidirectional, right? This could be going from your backend or from your cloud down to devices or vice versa. Today we're going to be looking primarily at data flowing from devices to your cloud. So why might you want to run WebAssembly at kind of each stage in the system here? Well, if you want to run it on something like Goliath, you're probably going to have a runtime provided for you. You're not under the constraints that you would have on a device, so having a runtime present is not something that's much of a concern. And you can provide optimization by perhaps filtering data or compressing it or something like that before it ends up on your cloud backend. You might want to run it on your cloud backend to have full control of how you're executing code. You might actually want to get, if you're building a product on top of a system like this, you might want to get WASM modules or code written by your customer to be able to run it against data in your backend, or take action on data, such as alerting, which is an example that we're going to look at today. And then you might want to do it on your device. We have a lot of customers and users who have cellular devices, and obviously when you're using cellular, you're concerned about bandwidth. So if you want to maybe reduce the amount of data that is sent over a cellular network, this could be a useful way to get some optimization there that may also be able to run in other environments. Okay, so getting to the title of the talk, we're going to look at WebAssembly on Zephyr, and I'm going to give a brief overview of one runtime that's kind of, in my approximation, really the most popular for embedded devices right now, and then we're going to jump into some code and look at how that actually works. So WebAssembly Micro Runtime, or WAMR, if you've been to other talks this week, it's come up a few times. This is under the Bytecode Alliance, which is where lots of the WebAssembly work happens. It's optimized for constrained environments. It's kind of in the name there. So the interpreter runtime size is about 85 kilobytes, which is not insignificant, but if you compare it to other runtimes, pretty incredible. It supports multiple execution models. So regular interpreted WebAssembly that we're familiar with, just-in-time compilation, and then what I mentioned earlier was ahead of time. So that's essentially where they have a compiler that they offer that allows you to take a WebAssembly module, compile it for the target, and then deliver that either in the custom section, which is what some runtimes do. WAMR, or WebAssembly Micro Runtime, actually has a different file format for that ahead of time compilation. And that's going to bring down your runtime size quite a bit if you're using native code. It also implements execute in place, which is extremely useful and is not something that's represented or implemented by all alternatives. So that's a really nice attribute that's available to you with Whammer. It also includes a Zephyr port, which is how I'm able to give you a demo today. And it's pretty close to being able to just be pulled in as a Zephyr module. And lastly, it supports WASI. This is not super useful today in the embedded ecosystem, but there's a lot of work that's happening in WASI to be able to expose things like SPI or I2C as standard interfaces. And so that's going to make this a lot more useful and also give you kind of a API to program against when you're writing WebAssembly modules that are intended to run in that environment. All right, so I'm going to stop talking up here at you with slides, and we're actually just going to look at implementing it. So in the demo that I'm going to give today, we're going to create a WebAssembly module that looks a lot like what we have in our example here, and we are going to run that kind of on either side of Goliath, the platform in the middle there, and we're going to use that to alert on temperature values. So starting off, here's the, if I jump out of here into the source, here is our example module that we looked at, where we can pass, in this case, it's going to be the temperature, and we're going to say if it's over 22 degrees, we're going to call that alert function. So I've already compiled this, but I'll go through the steps again, and we'll build it. So that goes pretty quick, and I am going to take this output, and we are going to base64 encode it. Let's see, simple WASM. And I'm going to use our setting service to basically put this onto a device here, which I'm going to start up in just a moment. So this is the console that we have, and I'm going to go in and change our existing WebAssembly module here. And we're not used to settings this large usually, but I'm going to go ahead and start up my device running here as well, which is an NRF 52840 development kit with an ESP32 for Wi-Fi. So that's going to start up, and we should see it connect here. And essentially what it's going to do is boot up, connect to this Wi-Fi network. It's going to fetch that WebAssembly module and then start going through a loop. And we're going to look at the actual code that it's executing. I'm also going to make this a little bit bigger here for y'all. Let me just go across and make sure. Is that big enough? Bigger? Good? All right, cool. So we can see here that we are streaming some temperature values, and then we have a alert that's happening for some of them, actually for all of them, which we're going to see. Any of them that are over 22, we should see an alert happening here. So this is the firmware that's running on the device. So up at the top, we have our alert function. So this is what we are going to import to our WebAssembly module that it can invoke. So in this case, all it's doing is saying whenever I get invoked, I log a message that says alert, and you could do something like blink a light or whatever you wanted in the context of your device. I'm going to go down to main here and see how we start up. First thing you're going to do with WebAssembly micro runtime is go ahead and instantiate or init the runtime. And there's a variety of settings you can provide there. One that we're going to provide is the native symbols, so the symbols to be imported to any module that we want to run. We're going to define how we want to allocate memory and a variety of other settings, and then initialize the runtime. And then loading the WASM module, I have one by default in this firmware binary that's just the bytes that it's going to load, and then it's going to start up and connect to Goliath, which is what we're doing here. Creates a co-op connection over DTLS, which is how we're able to fetch those settings and then stream our temperature data up to Goliath. We're also registering our setting there, which creates an observation. So anytime we update the content of our WebAssembly module, that is going to be observed by the device, pulled down, and then it's going to start invoking the new one instead. So our loop here is pretty simple. It's just looping through 5 values here and simulating like reading the temperature, streaming it up to Goliath, and then invoking the WASM module with whatever value it just streamed up. So that's great, but like I said, we also want to show this happening on the other side. So I'm going to start up a HTTP server here just locally, and what this is going to do is connect to Goliath over WebSocket and basically receive all of those streamed values that are coming from the device. And you're seeing here that I'm getting some alerts because it's also fetching that same WASM module and running it in what we could view here as the client application. So we're being able to use that consistent logic in 2 very different environments, right? A microcontroller and our browser here. And we might want to go in and change this over time. Obviously, this is a simple example where the value could just be, we're gonna stop this for just a second so that I can keep doing this demo. This is a simple example where you know, the value could be represented by a setting or something like that, but maybe you don't want to alert when you're calling it. I also wanted to show a bit of what's happening behind the scenes here in that simple web page. We're connecting, as I said, to Goliath to stream those values. And the important part here is that our alert function is calling a browser API instead of a device log message. But to the WASM module, right, it's programming against the interface that we've given it, which is just an alert function that takes no values and returns no values. Once again, a simple example, but it shows how, depending on where it's executing, the embedder can provide different functionality to it. So let's go ahead and change that and show the device picking it up. So I'm going to pick a value that's kind of in the middle of some of those temperatures. We'll say 65. I'm going to go ahead and recompile that, get the base 64 for it, and copy it up. That's not what we want. All right. So we'll change this to our new WASM module, and we should see that when we update that on the device, we have a new WASM module coming through here, and I'm going to restart this shortly because it looks like we had it recovered. Here we're seeing that we have a streaming temp, and when we invoke the WASM module, it's no longer alerting because it's under the value. And actually, yeah, I'm going to go ahead and restart this because I think it lost connection. But when it comes back up, we'll start iterating through those values, and we've changed the behavior so that it has a different response based on the value that's passed to it. And we can do the same on the web server side, pulling that in, 8,000 alert. And we should see temperature values start to stream through here as well. That first one was over 65, but all of them that are under are going to come through without our alerting logic. So we just see 48 come in under 65. So yeah, that's kind of an example of running a WebAssembly module in two very different contexts, but being able to provide different functionality in each. So with that, I'll open it up to any questions.
Thank you. So in that demo, was that an example of just-in-time compilation or ahead-of-time compilation?
It was actually neither. It was just interpreted.
Okay.
So yeah.
So in the just-in-time case, what exactly is the input and output of that compilation?
Yeah. So in the just-in-time case, the the input is just going to be the WASM module binary, and it will get compiled to native code on the fly on the device. And so, that can improve performance in some cases, especially if you're in kind of a tight loop there.
Thanks.
Yeah, hey, great talk. Couple questions for you. How big was the end WASM file that you had there that you had to pull over? It looked pretty small, base 64 encoded.
Yeah, I think it was 452 bytes.
That's pretty nice. And then I guess have you done any comparison with, like you write a C function that does some tight loop with math, you do a WASM function that does some tight loop with math, kind of like maybe a digital filter might, and compare and contrast kind of the performance difference?
Yeah, I haven't run any benchmarks. There are some in the WAMR repo, I believe, that some folks have done. But no, I haven't performed any myself.
Okay. Thank you.
We do have some online questions. So I think this is referring to the slide where you were showing the WASM running in all the different places.
Mm-hmm.
So the question is this like a combo of remote proc and WASM, i.e. push WASM code blobs to another processor core to run on the other side, or via networks, Wi-Fi, SPI, I2C, etc.? Are you aiming for that?
Can you say the beginning of that again?
Is this like a combo of remote proc and WASM, remote pros? Remote
okay.
PRIC?
Yeah. I guess sort of. That wasn't an explicit goal of the what I was demonstrating here. One of the things that I do think is interesting if you're using WASI and you have you leverage access to a SPI bus or something like that, is that's going to reduce some of the portability unless if you're able to simulate that in a browser environment or something like that. So it's not all translatable. There's portability is going to depend on what you're able to provide in each environment. So kind of the more you expand that interface you're programming against, the harder that may become.
Another one here. As WebAssembly continues to gain traction, how might it reshape the landscape of web development, and what opportunities does it present for developers, businesses, and the broader tech ecosystem?
That is sounds like it was from a corporate briefing, but I don't know how this is going to affect the life of web developers. I know that it's used in some performance critical web applications, and it's been useful in that context. I think that being able to run code against various different environments is useful. I will say that like one critique of this, and obviously I'm coming at this working at a platform company, is this really providing value to end users, or is this providing more value to the platform? And I think that's a fair question. Obviously, it's useful for us, for example, to be able to run code in a nice sandbox, but is that imposing more burden onto developers to have to learn WebAssembly and implement it and that sort of thing? I think it's a fair question to have.
Any more questions in the room?
Yeah, how would you go about, I mean, there's always bugs, even if you write it in Rust code, there's always going to be bugs. So how would you debug WASI on your device? Should it go ahead and blow up?
Sorry, can you say the end of that again?
Yeah, how would you go about debugging your WASM module on device? Should it fail?
Yeah, it's going to be more complex when you introduce an interpreter. So I think that's maybe something that wasn't referenced in the attributes, but something that's definitely a downside of bringing a runtime into your firmware. There are some there's some efforts in WAMR, I know, to make debugging a little bit easier. I think that's specifically focused on debugging the runtime. One of the ways that you can do that is you can pull exceptions out of the WebAssembly sandbox and view them in the embedder. But in terms of stepping through code in the interpreter, that's going to be a lot harder, and it's probably going to be dependent on the runtime providing you some hooks to be able to do that. So I would say it's a negative experience today.
Yeah. Thank you.
Curious if you've seen or looked at any comparisons kind of from a footprint size on like this versus MicroPython, or I know there was some Lua JIT or Lua work that was talked about a couple years ago with Zephyr.
Yeah, I haven't done any comparisons myself. I've read some online, but I think it's pretty use case dependent. So I wouldn't speak to any specific comparisons, but there are some available. Cool.
Any last questions?
Great. Thank you all for coming, and I hope everyone has a safe flight back. Thanks. I felt like it was pretty jumbled, but whatever.
There's a lot of information.
Yeah. It was pretty jumbled.